Hello there and welcome to Science for Sleep, where curiosity drifts gently into calm and the wonders of the universe take a soft, unhurried path toward your imagination. Tonight, we're going to explore a question that reaches to the very edges of existence. A question about the oldest things in the universe, the whispers of time that have travelled across eons to reach us. It's a gentle journey through age, light, and matter, through fragments of history older than our sun, older than the mountains, older than the planets. Imagine, if you will, tiny grains of cosmic dust that predate our Earth, atoms formed just after the first moments of creation, stars that have burned quietly for nearly the entire lifetime of the cosmos. It is astonishing in a way that something so ancient can still touch us, can still be studied, can still exist in the present moment, patiently waiting for our eyes, our instruments, and our thoughts to find them. Before we begin, I'm curious about you. Where are you listening from tonight? Are you tucked into a quiet room with a lamp casting a warm glow, or perhaps lying beneath the night sky, noticing the stars that themselves are relics of distant ages? The universe has a way of connecting us across space and time, and in this moment, wherever you are, you're sharing this contemplation with every observer, every quiet thinker who has ever looked upward and wondered about the origins of everything. And just like those ancient atoms, light and stars we're about to consider, your attention here is part of the journey, part of the story of time and existence. If you find this voyage calming or intriguing, if it offers a gentle pause from the rush of the day, a quiet way to explore the cosmos from the comfort of your own space, I would be ever so grateful if you liked this video and perhaps subscribed. It helps keep this small corner of calm alive, ready to share the slow wonders of science with others who might need a moment to breathe and reflect. There is no hurry here, no need to rush, only a gradual unfolding of knowledge, curiosity and quiet fascination, much like how the universe itself slowly reveals its secrets over billions of years. So, settle in and let your thoughts drift. Picture yourself not just in your chair or bed, but among the stars, tracing the faint glow of objects that have existed since the earliest moments of the cosmos. Let your mind follow the path of photons that have travelled for billions of years, bouncing from star to star, galaxy to galaxy, carrying the history of matter and light across distances so vast that they almost seem beyond comprehension. And yet, in this moment, they arrive, and you're here to witness them. The oldest things in the universe are patient. They do not rush, they do not demand attention. But when we notice them, they offer a perspective unlike anything else. As we begin to trace the history of these ancient elements, we will start with the idea of age itself in a cosmic context. When we speak of something being old, we often measure it in years, decades, or centuries. But when it comes to the universe, age is measured in millions, billions, and sometimes tens of billions of years. It's a scale that challenges our perception, that invites us to pause and stretch our imagination, to consider just how small our moments are in comparison. Stars, galaxies, and atoms have histories that stretch far beyond human experience, and yet they intersect with our lives in subtle ways, through the light that warms our planet, the elements that make up our bodies, and the gravitational dances that hold everything in balance. Even in our own solar system, we can find remnants of this ancient time. Meteorites that fall to Earth sometimes contain grains of matter older than the sun, tiny crystallized fragments that formed in other star systems before our solar neighborhood existed. These pre-solar grains are, in a sense, tangible memories of a universe that existed before the planets, before life, before human thought. Holding one, even in your imagination, is like holding a piece of the past itself, a fragment of history that survived eons of cosmic upheaval. Our exploration will also take us to the first stars, the so-called population 3 stars, which ignited in the darkness of the early universe. We cannot observe these stars directly, they have long since burned out, but their existence is inferred through the elements they produced, elements that would later seed galaxies and the formation of younger stars. These primordial stars were enormous, bright, and short-lived, and in their brief lives they forged the first heavy atoms, laying the groundwork for everything that came afterward. Without them, the universe as we know it, including every planet, every living organism, every atom in your body, would not exist. And in a very real way, by studying the oldest things, we are tracing our own cosmic ancestry. As we drift through this story, we will encounter not just stars, but galaxies that formed shortly after the Big Bang, galaxies whose light has travelled nearly 13 billion years to reach us. Each photon from these distant systems is a time capsule, a message from a universe still in its infancy, carrying information about conditions that existed when matter and energy were just beginning to arrange themselves into the structures we see today. It's a humbling reminder that the universe is far older, far larger, and far stranger than we usually imagine, and yet, in our calm attention, we can perceive a fragment of it, appreciate it, and let it deepen our sense of wonder. We will also consider objects that have persisted across billions of years in ways that feel almost magical. White dwarfs, the remnants of once vibrant stars, continue to glow softly for eons, cooling gradually as they fade into obscurity. Globular clusters, dense collections of ancient stars, orbit galaxies quietly, each star a witness to the history of the cosmos, each cluster a repository of memory. Even black holes, while invisible in themselves, are a record of the mass and energy that formed them, and their gravitational influence persists across cosmic time. Throughout this journey, we will touch on the tiniest pieces of the cosmos, the atoms that formed just minutes after the Big Bang. Hydrogen, helium, and traces of lithium floating through space, eventually condensed into stars and galaxies, eventually forming planets like ours. These atoms are older than the Earth, older than our Sun, and they still exist in every breath, every drop of water, every bit of stardust around us. Considering their age invites a reflection on how intimately connected we are to the universe and to the oldest matter within it. As you listen and imagine, you may notice a subtle shift in your own sense of time. While we discuss eons, you remain here, in your own moment, simultaneously participating in the history we trace. That dual perspective of your human immediacy and the timelessness of cosmic matter is part of what makes contemplating the oldest things in the universe so profoundly soothing. It reminds us that while life is fleeting, there are threads of continuity that stretch far beyond our perception, threads that we can touch through thought, imagination, and attention. When we speak of age in everyday life, it usually feels straightforward. A birthday marks another year, a tree can be measured by its rings, and objects around us carry dates we can easily track. But when we move into a cosmic context, the notion of age becomes something much more expansive, much more subtle and far less intuitive. It stretches our minds and our imagination, because the universe operates on scales that dwarf human experience. Billions of years pass in what feels like a single moment, and events that shape the cosmos unfold over epochs so long that our usual methods of measurement seem almost laughably small. In our human world, time is often linear, neatly packaged into minutes, hours, and years. We can recount history, track progress, and mark the passage of time in ways that feel tangible and familiar. Yet the universe does not adhere to our clocks or calendars. Its processes are guided by forces, chemistry, gravity, and the interactions of matter and energy, all operating independently of human perception. A star can live for millions or even billions of years, its life and death entirely detached from our schedules, and yet its legacy, the light it emits, the elements it creates, the gravitational imprint it leaves, persists long after it vanishes from sight. The concept of age in this setting is not just a number, it is a story, a record of change, a measure of persistence across unimaginable scales. To consider cosmic age, we must first think about how we measure time on a universal scale. One of the primary tools astronomers use is light itself. Light travels at a fixed speed, around 299,792 kilometers per second, and it moves steadily across the void of space. When we observe distant objects, we are not seeing them as they are now, but as they were when the light began its journey toward us. A galaxy, 1,000,000 light-years away, is seen as it was 1,000,000 years ago, meaning that each glance into the night sky is a form of time travel. In a sense, every observation becomes a window into the past, and the farther we look, the older the things we see. This is why the universe offers a kind of cosmic diary, a record that allows us to trace back through its history in layers of light. Yet measuring age by light is only part of the story. Stars themselves serve as natural clocks. Their internal processes, governed by nuclear fusion, follow predictable patterns. By examining the composition and energy output of a star, astronomers can estimate its age with remarkable precision. The colour, brightness, and spectrum of a star provide clues about how long it has been burning, how far along it is in its life cycle, and how much fuel remains before it either collapses, explodes, or fades into obscurity. Some of these stars are unimaginably old, born not long after the first light of the universe emerged. They carry the chemical fingerprints of earlier generations, forged in the fiery crucibles of stars that no longer exist. Even more fundamental than stars are the atoms themselves. The simplest atoms, hydrogen, helium, and traces of lithium, formed during the first few minutes after the Big Bang. These primordial elements have persisted for over 13 billion years, circulating through space, becoming part of stars, planets, and eventually life itself. Each atom is a record of the early universe, a survivor of a time when matter first began to coalesce and the cosmos transitioned from a hot, dense plasma into the more structured universe we see today. Their age is not abstract. It is tangible in the way these atoms interact, bond, and eventually participate in the formation of everything that exists. To grasp the vastness of cosmic time, it can help to scale it down in a way that makes it slightly more relatable. If we imagine the universe's history compressed into a single year, the formation of Earth would occur on December 31st, just hours before midnight. Human history would then occupy only the last few seconds of that final day. In this framework, the oldest things in the universe existed long before our planet was formed, long before our species, long before our solar system even coalesced from a cloud of gas and dust. The perspective it provides is humbling and grounding, reminding us that while our lives are short, they are part of an ongoing story stretching back to the first moments of creation. Age in the cosmic context also forces us to confront the impermanence of familiar objects. Stars burn out, galaxies collide and merge, and black holes absorb matter until it disappears from view. Even objects that seem eternal on human timescales are transient on the cosmic clock. What we consider old on Earth, a 1,000-year-old tree, an ancient ruin, a fossilized skeleton, is almost instantaneous compared to the life of stars or the persistence of interstellar matter. Understanding this difference allows us to perceive age not just as a number, but as a measure of endurance, a reflection of processes that continue long after our immediate experience has ended. When we look at the oldest things, we must also consider their journey through space. Light from distant galaxies travels billions of years before reaching our telescopes. Even within our own galaxy, matter moves, orbits, and interacts with other bodies, carrying with it a story of formation, transformation, and survival. Dust grains, forged in the atmospheres of dying stars, drift through the galaxy for billions of years, eventually becoming incorporated into new stars or planets. Meteorites that fall to Earth may contain these ancient grains, tiny fragments of matter that predate our solar system, allowing us to hold a tangible piece of cosmic history in our hands. In this sense, age is not merely a chronological measure. It is a map of interactions, migrations, and transformations that span both space and time. Age also connects intimately with entropy, the measure of disorder that governs much of the universe's evolution. High entropy systems, those in which energy is spread out and disorder increases, define the arrow of time. Older objects in the universe have experienced more interactions, more processes that contribute to entropy. Their state today reflects not just how long they have existed, but the ways in which they have interacted with their surroundings, the changes they have undergone, and the remnants they have left behind. Entropy links age with transformation, emphasizing that being old in the cosmos often means having endured change, having participated in the slow unfolding of the universe's story. Some of the oldest objects we can study are actually the remnants of stars that have long since died. White dwarfs, neutron stars, and even black holes carry information about earlier times. White dwarfs cool gradually over billions of years, allowing astronomers to estimate their ages with precision. Globular clusters, dense collections of ancient stars orbiting the outskirts of galaxies, contain members that formed shortly after the first generations of stars, providing a record of the universe's early development. In every case, the age of these objects is not a simple number, but a layered story of formation, evolution, and survival. Even the fabric of space itself has an age. The cosmic microwave background, a faint glow permeating the universe, is the oldest light we can observe. It dates to roughly 380,000 years after the Big Bang, carrying the imprint of the universe's earlier structures and the conditions that existed when matter first became transparent to radiation. Studying it allows scientists to infer not just the age of the universe, but the processes that shaped it, the distribution of matter, and the seeds from which galaxies would eventually form. This light is a direct witness to the earliest moments of existence, a kind of cosmic fossil that has travelled across the universe for nearly 14 billion years, arriving in our detectors as a silent testimony to the deep past. Age in a cosmic context is also shaped by relativity. Time itself is not a uniform measure across the universe. It can stretch, slow down, or accelerate depending on gravity and velocity. An object near a massive body experiences time slightly differently than one farther away. Even at small scales, these differences become measurable with precise atomic clocks, and at cosmic scales they become essential for understanding the evolution of ancient stars, galaxies, and the remnants of the earliest matter. Age is not absolute in the universe, but a relational measure, a story told by the interactions between matter, energy, and space-time itself. Our understanding of cosmic age has been built over centuries, beginning with careful observations of the night sky, the measurement of stellar motions, and the development of physics that allows us to interpret the light we receive. The oldest stars were discovered through spectroscopy, their composition revealing the absence of heavier elements, confirming that they formed before subsequent generations enriched the universe with metals. Radiometric dating of meteorites provided clues about the age of the solar system and its components, revealing that matter in our neighbourhood of space has persisted for over 4.5 billion years. Each method, whether it involves light, matter, or gravitational interactions, contributes to a layered understanding of age, showing that even in the vast, seemingly empty cosmos, time leaves its traces. And so, age in the cosmic context becomes not just a measure of how long something has existed, but a reflection of the processes it has witnessed, the transformations it has undergone, and the interactions it has participated in. To consider the oldest things in the universe is to consider history on a scale so vast that it challenges human perception. Yet in doing so, it also deepens our sense of connection, reminding us that even the youngest of us is built from the remnants of ancient stars and atoms that have endured billions of years. By understanding age this way, we begin to see a continuum, a tapestry woven from the earliest light, the first atoms, the oldest stars, and the enduring remnants of cosmic processes. Each piece of matter, each photon, Each gravitational ripple contributes to this story, linking the ancient with the present. As we begin to consider how we observe the oldest things in the universe, it helps to understand that every glimpse into the cosmos is also a glance into the past. Light, travelling at a finite speed, is much more than a means to illuminate objects. It is a messenger that carries with it the story of what has already happened. When we gaze at the night sky, the stars we see may have lived, burned, and died long before the first humans walked the Earth. Each photon that reaches our eyes has endured a journey across space, perhaps spanning millions or even billions of years, carrying with it the memory of the moment it was emitted. It is both humbling and quieting to realize that our act of seeing is inherently an act of time travel, a connection to events far removed from our immediate experience. The concept of light as a cosmic messenger begins with understanding its speed and constancy. Photons, the particles of light, move at roughly 299,792 kilometers per second in a vacuum, a pace so unchanging that it allows astronomers to measure distances and times with remarkable precision. When we say a galaxy is 10 million light-years away, what we are really saying is that the light leaving that galaxy took 10 million years to reach us. That light shows us the galaxy not as it is today, but as it was 10 million years ago. In essence, looking at distant objects is a form of looking backward, where the deeper we peer into space, the farther back we see in time. This idea transforms our understanding of observation from a simple act of vision into an exploration of history, where every beam of light is a witness carrying a story frozen at the moment of departure. Even within our own galaxy, the light we observe can reveal incredible age. Stars at varying distances send their photons to us, each reflecting conditions from the moment they ignited. Some of these stars are members of globular clusters, dense spherical collections of ancient stars whose ages often exceed 10 billion years. The light from these stars allows scientists to reconstruct the properties of early stellar generations, the processes that form the first heavy elements, and the gravitational interactions that shape the galaxy. Observing them is like reading a history book written in wavelengths and intensities, each measurement translating into the age and evolution of objects that have persisted across nearly the entirety of cosmic time. Beyond the stars within our own galaxy, the same principle applies to entire galaxies. When we observe the faint glow of a galaxy billions of light-years away, we are witnessing it as it existed in a much younger universe. Its structure, its star formation, and its composition are all frozen in that light, providing clues about the environment in which it formed, the dynamics that influenced its growth, and the elements it produced. Some of these distant galaxies are so remote that their light began its journey when the universe was less than 1 billion years old, offering a glimpse into an epoch where the first stars and galaxies were just beginning to emerge from cosmic darkness. Through careful analysis, astronomers can trace the evolution of galaxies, connecting the earlier structures to the universe we inhabit today, all by following the journey of photons across unimaginable distances. In addition to visible light, other forms of electromagnetic radiation play a crucial role as cosmic messengers. Infrared, ultraviolet, X-rays and radio waves all travel across space, each carrying information about different processes and environments. Infrared light, for instance, allows us to peer through interstellar dust, revealing star formation hidden from optical telescopes. Radio waves can trace the distribution of hydrogen gas, the primary ingredient for future stars, while X-rays highlight the presence of extremely energetic phenomena, such as the accretion of matter onto black holes. Each of these forms of light provides a unique historical record, capturing events at different times, from different places, and under different conditions. Together, they allow us to construct a more complete picture of the universe's history, all through the patient arrival of ancient signals. One of the most striking examples of a light-carrying history is the cosmic microwave background, the faint afterglow of the Big Bang. This radiation has been travelling for nearly 13.8 billion years, filling the universe and offering a snapshot of the cosmos when it was only a few 100,000 years old. It reveals minute fluctuations in temperature and density that would later guide the formation of galaxies and large-scale structure. By studying this primordial light, scientists can infer the age, composition and geometry of the universe itself. In this sense, the cosmic microwave background is not just light. It is the oldest visible record we can observe, a relic from the infancy of the cosmos, a whisper from a time long before stars, planets or life existed. Even when observing individual stars or galaxies, the finite speed of light introduces a fascinating paradox. The oldest stars we can see may already be dead. Their light continues to travel, allowing us to witness their existence after their life cycle has ended. A star may have collapsed into a white dwarf or exploded as a supernova, yet its light still carries information from a time when it shone brightly. This means that the oldest things we observe are not necessarily alive in the present sense. Their persistence in our observations is a result of the slow, steady journey of light across space. The universe thus presents a layered reality, where the age of an object, the distance it resides at, and the light we detect all intertwine to produce a complex overlapping chronology of cosmic history. When we measure these distances and ages, we also encounter the effects of cosmological expansion. As space itself stretches, light travelling from distant galaxies is red-shifted, its wavelength elongated by the expansion of the universe. This redshift provides a direct measure of how far the light has travelled and indirectly how long ago it was emitted. Through this technique, astronomers can identify galaxies that formed very early in cosmic history, helping us pinpoint the oldest observable structures. Each measurement is a delicate balance between the physics of light, the geometry of space-time, and our models of the universe's growth, a testament to both the precision of human observation and the vast patience of the cosmos itself. Even within the confines of our solar system, light serves as a messenger of age. Consider the ancient meteorites that fall to Earth. These rocks carry isotopes whose decay rates are well known, allowing scientists to date them accurately. They often contain pre-solar grains, microscopic fragments of stars that existed before the sun formed. The light reflected from these grains, combined with their composition, tells a story that spans billions of years, revealing conditions in distant stellar nurseries and the processes that created the first elements heavier than hydrogen and helium. Observing and studying these grains is a tangible encounter with the universe's oldest matter, a direct connection to events that occurred long before Earth itself came into being. Our understanding of light as a cosmic messenger also extends to extreme environments. Supernovae, for instance, are explosions of massive stars that scatter newly formed elements across space. The light from these events carries information about the star's mass, composition, and the energy released in the explosion. Some supernovae have been observed in distant galaxies, meaning their light has travelled billions of years to reach us. In essence, when we observe these supernovae, we are seeing the death of a star in the remote past, the creation of elements that will one day become part of new stars, planets, or even life itself. Light preserves this record, allowing us to study processes that occurred long before our own existence. Cosmic messengers are not limited to photons. Neutrinos, nearly massless particles, also travel across space at nearly the speed of light, often escaping dense environments that light cannot penetrate. They carry information about the most energetic events, such as supernovae or collisions between neutron stars. Detecting these particles allows scientists to complement observations made with light, providing a richer understanding of events that shaped the early universe and the oldest objects within it. Each particle is a messenger, moving steadily across cosmic distances, offering insights into the processes that have unfolded over billions of years. By tracing light and other messengers, we begin to piece together a chronology of the universe. The oldest stars, the first galaxies, the primordial gas, and the ancient cosmic background all offer layers of information, stacked like pages of an unwritten history book. Each observation connects to the next, revealing a story that spans from the first moments after the Big Bang to the structures we can see today. Age, distance, and observation intertwine, creating a timeline that extends far beyond human experience, yet one that we can perceive and understand through careful attention and patient measurement. Even the act of observation carries a subtle reflection on time. By pointing a telescope, turning a detector toward a distant point in the sky, we are engaging with history. Each measurement is a conversation with the past, where photons that have travelled for millions or billions of years meet the instruments we have built to interpret them. Every spectrum, every image, every signal is both a scientific record and a quiet reminder of the persistence and endurance of matter and energy across cosmic time. Light becomes the bridge between what was and what we can know, a delicate link that allows us to experience the ancient universe as it unfolds through careful study. The more we consider light as a messenger, the more we appreciate that the oldest things in the universe are not just static relics, but dynamic participants in an ongoing story. Stars burn, die, and seed new generations. Galaxies collide, merge, and transform. Atoms cycle through stars, planets, and living beings. The light reaching us today is evidence of these processes, a record of change that has been travelling for eons, arriving in the present moment for our reflection. This connection reminds us that while human life is brief, it intersects with an astonishingly ancient cosmos, and through light, we can touch and understand the oldest things that persist across the vast stretches of space and time. Light is our guide, a patient companion, and a storyteller that delivers the universe's history to us gently without hurry, across distances and epochs that challenge comprehension yet invite contemplation. As we follow the journey of light across the vast expanses of space, we encounter one of the oldest and most enduring signals in the universe, the cosmic microwave background, or CMB. This faint glow pervades every corner of the cosmos, a relic from the earliest epoch we can observe, carrying information about the universe as it existed nearly 13.8 billion years ago. It is not light from a star, nor from a galaxy, but a residual signal from the time when the universe first became transparent, when the dense plasma of protons and electrons cooled enough to allow photons to travel freely for the first time. This ancient radiation is, in essence, the universe's oldest observable memory, a snapshot of matter and energy before stars, before galaxies, before planets, and long before life as we know it emerged. To understand the cosmic microwave background, it helps to recall the conditions of the early universe. Immediately following the Big Bang, the cosmos was an extremely hot, dense soup of particles, radiation, and energy. At this stage, photons could not travel far without being scattered by free electrons, so the universe was opaque, like a thick fog through which nothing could pass. As the universe expanded, it cooled, and after roughly 380,000 years, the temperature dropped enough for electrons and protons to combine and form neutral hydrogen atoms. With electrons bound, photons no longer scattered incessantly, and the universe became transparent. These photons, which had been trapped for hundreds of thousands of years, suddenly began travelling freely, carrying with them the imprint of the density fluctuations present at that time. These fluctuations would later guide the formation of galaxies and large-scale structures. The CMB is remarkably uniform, filling space almost evenly, but careful observations reveal tiny variations in temperature, on the order of 1 part in 100,000. These fluctuations are critical because they encode the earliest information about the universe's structure. Some regions were slightly denser, eventually collapsing under gravity to form stars and galaxies, while less dense regions became the vast voids we observe today. Studying these variations allows scientists to reconstruct the conditions of the early universe, to understand its composition, its expansion rate, and even the amount of matter and dark matter present. Each subtle ripple in the cosmic microwave background is like a fingerprint of the young universe, frozen into the radiation that continues to reach us today. Detecting the CMB is not simple. Because it has cooled over billions of years, it no longer exists in the visible spectrum, but rather in the microwave range of the electromagnetic spectrum. Specialized instruments, both on satellites and ground-based observatories, are required to measure its faint glow and map its temperature variations across the sky. The data collected over decades from missions like COBE, WMAP, and Planck have revealed the CMB's uniformity and subtle structure with incredible precision. These measurements have confirmed the Big Bang model of cosmology, allowed us to calculate the age of the universe, and provided insight into the earliest moments of cosmic history. Each observation is a direct engagement with photons that have travelled across the universe for nearly its entire existence, a bridge connecting the present with a time before stars or galaxies existed. One of the most striking aspects of the CMB is the sheer age of the photons themselves. Every particle of light in this background has been travelling since the universe was only a few 100,000 years old. That means the light reaching our telescopes today has endured the expansion of space, the formation and collapse of stars, the collision and merging of galaxies, and the rotation of our own Milky Way, all without losing the information it carries about its original conditions. When we detect this radiation, we are literally observing the universe as it existed in its infancy, long before planets formed, long before life emerged, and long before human consciousness could even conceive of the cosmos. This light is the oldest tangible signal we can study directly, a constant reminder of the persistence of matter and energy across incomprehensible timescales. The variations in the CMB also tell a story about the universe's composition. By analysing the patterns of hotter and cooler regions, scientists can infer the relative amounts of ordinary matter, dark matter, and dark energy. Ordinary matter, the kind that makes up stars, planets, and people, is only a small fraction of the total content of the universe. Dark matter, invisible yet influential through gravity, makes up a significant portion, guiding the formation of structures over billions of years. Dark energy, mysterious and still poorly understood, drives the accelerating expansion of space. The cosmic microwave background acts as a record of these components, offering insight into their proportions and their effects on cosmic evolution. Through it, we can see how the universe developed from a nearly uniform plasma into the rich, structured cosmos we observe today. Observing the CMB is also a reminder of the universality of age in the cosmos. Unlike stars which form, live, and die on individual timescales, the CMB pervades all space. Every point in the universe contains these ancient photons, making it a truly omnipresent relic of cosmic infancy. Whether we measure the CMB from Earth, a satellite orbiting above the atmosphere, or a distant probe, we are always encountering the same radiation that has been travelling since the earliest times. It is a shared history, connecting every corner of the observable universe to a single event, the moment when the universe became transparent to light. The CMB also helps us understand the rate of the universe's expansion. Observing its redshift, the stretching of its wavelength as space expands, provides information about how quickly the universe has grown over time. By comparing the CMB's properties to models of cosmic evolution, scientists can estimate the universe's age, currently calculated to be approximately 13.8 billion years. In this way, the oldest light does not just provide a record of conditions long ago, but also acts as a tool for measuring the passage of cosmic time, helping us place other ancient objects and events into chronological context. Even more intriguing is the information encoded in the polarization of the CMB. Tiny twists in the orientation of the radiation, caused by interactions with matter and gravitational waves in the early universe, allow scientists to probe conditions at times far earlier than the formation of the first atoms. These polarization patterns may reveal the influence of primordial gravitational waves, ripples in space-time generated during cosmic inflation, a rapid expansion that occurred a fraction of a second after the Big Bang. Through these measurements, the CMB offers a window into events that are otherwise inaccessible, a messenger carrying secrets from the first moments of existence. The CMB is also a reminder of the scale of the universe and our position within it. These photons have travelled across billions of light years, passing through intergalactic space, interacting only minimally with the matter they encounter. Each particle of light has witnessed the formation of structures, the birth and death of stars, the swirling of galaxies, and yet it continues toward us largely unaltered. Observing this radiation gives us perspective, connecting us not just with distant objects, but with the very timeline of the universe. It emphasizes the continuity of matter and energy, showing that the oldest signals are still present, still accessible and still meaningful, even in a universe constantly in motion and change. By following the cosmic microwave background, we're also tracing the roots of the oldest matter. The density fluctuations imprinted in the CMB guided the formation of the first stars and galaxies, and the atoms forged in those stars continue to exist today. The CMB is thus a direct link between the universe's beginning and the ancient objects we will encounter later. The oldest stars, the pre-solar grains, the remnants of long-dead stars, and even the atoms that ultimately became part of Earth. Through this radiation, we begin to see how ancient matter has endured, how it has travelled, and how it has contributed to the universe we inhabit. The importance of the CMB extends beyond observation. It forms the foundation for modern cosmology, providing a benchmark against which all other measurements of age and distance are calibrated. By understanding this radiation, scientists can refine models of galaxy formation, star evolution, and cosmic expansion. Each observation, each map of temperature and polarization, contributes to a larger understanding of how the universe evolved from a hot, dense plasma into the structured cosmos we see today. In this sense, the oldest light is not merely a curiosity, it is the framework upon which our comprehension of cosmic history rests. Even as we focus on this radiation, it is worth remembering that the universe contains layers upon layers of ancient objects. While the CMB represents the oldest light, other relics such as primordial atoms, presolar grains, and long-lived stars offer complementary records of cosmic history. Together, these pieces create a tapestry of age, survival, and transformation. The cosmic microwave background is the first page in this story, a faint yet persistent whisper from a time before stars, before galaxies, and before the structures that now dominate the observable universe. It teaches patience, endurance, and the remarkable continuity of matter and energy across incomprehensible time. In contemplating the CMB, we also confront the limits of our perception. Human senses cannot detect microwaves directly, and our technology is required to translate the faint signals into information we can study. This reminds us that engaging with the oldest things in the universe often requires tools that extend our natural abilities. Telescopes, detectors, satellites, and computational models become extensions of our perception, allowing us to experience phenomena that are otherwise imperceptible. Through these instruments, we can study the faint whisper of the universe's infancy, bridging the gap between our immediate experience and the ancient cosmos. And so, by observing the cosmic microwave background, we gain more than information about the early universe. We encounter the first truly ancient signals that are still detectable today, tracing their journey across space and time. We see the conditions that gave rise to the first stars and galaxies, the earliest arrangements of matter, and the fundamental processes that shape the cosmos. Long before galaxies settled into their familiar spirals and clusters, before planets cooled and oceans formed, the universe passed through a quiet, dark period where light itself had yet to take hold in the way we recognize today. After the release of the cosmic microwave background, the universe became transparent, filled with vast clouds of hydrogen and helium drifting through expanding space. There were no stars yet, no galaxies, no points of light to punctuate the darkness. This era is often described as the cosmic dark ages, not because nothing existed, but because nothing shone. Matter was present, gravity was at work, and time continued its steady progression, but illumination had not yet begun in earnest. Gradually, almost imperceptibly at first, small irregularities in the density of matter began to grow. Regions that were slightly denser than their surroundings started to pull in more material through gravity. Over millions of years, these concentrations became more pronounced, gathering gas and compressing it into tighter and tighter spaces. As this gas collapsed, it heated up, its particles moving faster and colliding more frequently. Eventually, in some of these dense pockets, conditions reached a critical point where nuclear fusion could ignite. When that happened, the first stars were born. These earlier stars, known as population 3 stars, were unlike the stars we see today. They formed from a universe that contained only the simplest elements, primarily hydrogen and helium, with almost no heavier elements at all. This lack of heavier elements had profound consequences for their structure and behaviour. Without elements like carbon, oxygen, or iron to help cool the collapsing gas, the clouds that formed these stars tended to grow very large before they could ignite. As a result, many of the first stars were enormous, often dozens or even hundreds of times more massive than our Sun. Their size influenced everything about them. Massive stars burn their fuel quickly, producing intense amounts of energy and radiation. The first stars likely shone with extraordinary brightness, their light cutting through the darkness that had persisted since the early universe. Yet despite their brilliance, their lives were short. While smaller stars like our Sun can burn steadily for billions of years, these early giants lived for only a few million years before exhausting their fuel. In cosmic terms, that is a brief existence, a flash of activity in an otherwise long and unfolding story. When these massive stars reached the end of their lives, they did not simply fade away. Many ended in powerful supernova explosions, releasing enormous amounts of energy and scattering newly formed elements into the surrounding space. This was a crucial turning point in the history of the universe. The first stars were responsible for creating the first elements heavier than helium, elements like carbon, oxygen, and iron. These elements would later become the building blocks of planets, of complex chemistry, and eventually of a life itself. In that sense, the first stars were not just sources of light, but creators of the material that would shape everything that followed. Their explosions also had another effect. The energy released by these supernovae pushed surrounding gas outward, influencing the formation of future stars and galaxies. Regions that might otherwise have remained dense and stable were disrupted, while other areas were enriched with heavier elements, making it easier for subsequent generations of stars to form. Over time, this process led to the emergence of more complex stellar populations, with stars of varying sizes, compositions, and lifespans. The universe began to transition from simplicity to diversity, guided by the cycles of star formation and destruction initiated by these first luminous objects. Despite their importance, none of these original stars remain today. Their short lifespans mean they have long since disappeared, leaving behind only indirect evidence of their existence. Astronomers infer their presence by studying the composition of later stars, particularly those that contain very low amounts of heavy elements. These ancient stars, sometimes called extremely metal-poor stars, preserve the chemical signatures of the earlier stellar generations. By analysing their spectra, scientists can piece together the characteristics of the first stars, reconstructing their masses, their lifespans, and the types of elements they produced. There is something quietly remarkable about this method of discovery. Rather than observing the first stars directly, we read their legacy in the objects that followed. It is a bit like understanding an ancient civilization through the artifacts it left behind, even when no direct records survive. The universe keeps its history in layers, with each generation of stars carrying traces of those that came before. By examining these layers carefully, we can extend our understanding back to times far beyond direct observation. The first stars also played a role in shaping the large-scale structure of the universe. Their radiation ionized the surrounding hydrogen gas, stripping electrons from atoms and making the universe more transparent to certain wavelengths of light. This period, known as the Epoch of Rionization, marked a significant transition in cosmic history. As more stars formed and more radiation filled space, the fog of neutral hydrogen that had dominated the early universe began to clear. This allowed light to travel more freely, making it possible for galaxies to become visible across vast distances. During this time, small clusters of stars began to form larger structures, eventually giving rise to the first galaxies. These early galaxies were likely irregular and chaotic, shaped by the interplay of gravity, radiation, and the remnants of earlier stars. Over billions of years, they would evolve into the more organized forms we see today, with spiral arms, elliptical shapes, and intricate patterns of star formation. The seeds of these structures, however, were planted by the first stars, whose influence extended far beyond their brief lifetimes. It is also worth considering how different the night sky would have looked during this era. Before the first stars ignited, there would have been no visible points of light, only darkness stretching in every direction. When the first stars appeared, they would have been isolated and scattered, gradually increasing in number as more regions of gas collapsed and ignited. Over time, clusters and galaxies would have formed, filling the sky with light and creating the complex patterns we now observe. The transformation from darkness to a universe filled with stars is one of the most profound changes in cosmic history, and it began with these earlier sparks. Even though the first stars themselves are gone, their influence continues to shape the universe today. The elements they produced are found in later generations of stars, in planets, and in the very matter that makes up living organisms. The carbon in your body, the oxygen you breathe, and the iron in your blood all trace their origins back to processes that began with stars like these. While not all of these elements were created by the very first stars, those early stellar generations set the stage for the ongoing cycle of creation and transformation that continues to this day. Modern telescopes, including space-based observatories, are beginning to detect galaxies that formed not long after these first stars appeared. By studying these distant galaxies, astronomers can observe conditions that resemble those of the early universe, providing indirect insights into how the first stars might have behaved. Each new observation adds to our understanding, refining models and revealing details that were previously hidden. It is a slow process, requiring patience and careful analysis, but it continues to bring us closer to understanding these ancient objects. There is also an interesting connection between the first stars and the oldest surviving stars we can observe today. Some stars in our galaxy are nearly as old as the universe itself, having formed from material that was only slightly enriched by earlier generations. These stars serve as living records, preserving information about the conditions that existed shortly after the first stars completed their life cycles. By studying them, we can trace a continuous line of history from the earliest moments of star formation to the present day. In a broader sense, the story of the first stars highlights the interplay between simplicity and complexity in the universe. Starting from a nearly uniform distribution of hydrogen and helium, gravity and nuclear physics combine to create luminous objects capable of producing a wide range of elements. These elements then contributed to the formation of more complex structures, leading eventually to planets and life. The process is gradual, unfolding over billions of years, yet each step builds on the last, creating a chain of events that connects the earlier stars to everything that exists today. Considering the first stars also invites reflection on the nature of beginnings. These objects marked the transition from a dark, featureless universe to one filled with light and structure. They were the first engines of change, initiating processes that would continue across cosmic time. While they no longer exist, their impact is still visible in the composition of matter, the formation of galaxies, and the distribution of elements throughout the universe. Their story is not one of permanence but of influence, showing how even brief events can have lasting consequences on a grand scale. Across the expanding darkness of the early universe, something remarkable began to take shape. Not isolated points of light anymore, not just the brief, intense lives of the first stars, but vast gatherings of matter bound together by gravity, forming structures that would endure for billions of years. These were the first galaxies, collections of stars, gas and dark matter that emerged as some of the earliest large-scale structures in the cosmos. If the first stars were sparks, then galaxies became the steady lanterns, glowing across space, carrying forward the work those early stars had begun. At first glance, a galaxy might seem like a simple idea, just a group of stars held together. But in reality, each galaxy is a complex system, shaped by gravity, motion, and the accumulation of matter over time. In the earlier stages of the universe, galaxies did not look like the familiar spirals or smooth ellipticals we often picture today. Instead, they were smaller, more irregular, and far more chaotic. Gas clouds collided, stars formed rapidly, and gravitational interactions constantly reshaped their structure. These early galaxies were active places where the processes initiated by the first stars continued on a larger scale. Understanding these ancient galaxies depends, once again, on light. The ones we observe today at great distances are not being seen as they exist now, but as they were billions of years ago. Some of the galaxies detected by modern telescopes are so distant that their light began travelling toward us when the universe was only a few 100 million years old. This places them among the oldest observable structures, making them crucial for understanding how the universe evolved from its earliest stages into the rich and varied cosmos we see today. The light from these galaxies is often faint and stretched into longer wavelengths due to the expansion of space. This redshift shifts their light out of the visible spectrum and into the infrared, requiring highly sensitive instruments to detect them. Observatories such as the James Webb Space Telescope have been designed specifically to capture this ancient light, allowing astronomers to study galaxies that formed not long after the first stars. These observations provide a direct glimpse into the universe's early history, revealing structures that existed when the cosmos was still in its formative stages. One of the most striking aspects of these early galaxies is how quickly they appear to have formed. Given the relatively short time after the Big Bang in which they are observed, their size and complexity can be surprising. Some contain billions of stars, suggesting that star formation in the early universe was both rapid and efficient. This challenges earlier assumptions about how long it would take for galaxies to assemble, and indicates that the processes driving their formation were highly effective, even under the simpler conditions of the early cosmos. These galaxies are often described as islands of light, not in a poetic sense, but in a very literal one, surrounded by vast regions of space that contained relatively little structure. They stood out as concentrated sources of radiation and matter. Within them, stars formed, lived, and died, enriching the surrounding gas with heavier elements. Over time, these galaxies would merge with others, grow in size, and evolve into the more familiar forms we see today. Each one represents a node in the expanding network of cosmic structure, a place where matter gathered and complexity increased. Their formation is closely tied to the distribution of dark matter, an invisible component of the universe that exerts gravitational influence without emitting light. In the early universe, dark matter formed a kind of scaffold, creating regions where ordinary matter could accumulate. Gas fell into these gravitational wells, cooling and condensing until stars began to form. The galaxies we observe are in many ways shaped by this unseen framework, their positions and movements reflecting the distribution of dark matter that surrounds them. The age of these galaxies can be inferred through several methods, including their redshift, their stellar populations, and their chemical composition. Galaxies that formed earlier tend to have stars with fewer heavy elements, as there had been less time for successive generations of stars to produce and distribute those elements. By analysing the spectra of light from these galaxies, astronomers can determine how enriched they are, providing clues about how many cycles of star formation they have undergone. This allows scientists to place them within the timeline of cosmic history, identifying those that formed closest to the beginning. Some of the earliest galaxies also exhibit intense bursts of star formation, sometimes referred to as starburst activity. In these environments, gas is rapidly converted into stars, producing large amounts of light and energy. This can make young galaxies appear brighter than expected despite their great distance. These bursts are often triggered by interactions or mergers with other galaxies, events that compress gas and stimulate the formation of new stars. Even in the early universe, where galaxies were smaller and more irregular, these interactions played a key role in shaping their evolution. As these galaxies evolved, they began to develop more stable structures. Over billions of years, some formed rotating disks, giving rise to spiral galaxies, while others became more spherical, forming elliptical galaxies. The processes that determine these shapes involve a combination of angular momentum, mergers, and the distribution of matter within the galaxy. Observing ancient galaxies at different stages allows astronomers to piece together how these structures emerged, tracing the transition from chaotic beginnings to more orderly forms. It's also important to consider that not all early galaxies survived unchanged. Many merged with others, combining their stars, gas, and dark matter into larger systems. These mergers are a fundamental aspect of galaxy evolution, leading to the formation of massive galaxies over time. Our own Milky Way, for example, is believed to have grown through a series of such mergers, incorporating smaller galaxies into its structure. In this sense, ancient galaxies are not just relics. They are building blocks, contributing to the ongoing assembly of larger cosmic systems. The study of these galaxies also provides insight into the conditions of the early universe. By examining their size, shape, and distribution, scientists can test models of cosmic evolution, refining our understanding of how matter behaved under the influence of gravity and expansion. Each observation acts as a data point in a larger picture, helping to answer questions about how quickly structures formed, how they interacted, and how the universe transitioned from simplicity to complexity. Even though these galaxies are incredibly distant, their light still reaches us, carrying with it the imprint of their past. This creates a layered view of the universe, where nearby galaxies show us more recent history, while distant ones reveal earlier stages. By combining observations across different distances, astronomers can construct a timeline of galaxy formation, mapping out how these islands of light appeared, grew, and transformed over billions of years. It is a form of cosmic archaeology, where each discovery adds another piece to the story. There is also a subtle connection between these ancient galaxies and the matter we encounter much closer to home. The elements produced within early galaxies eventually spread throughout space, becoming part of new stars, planets, and even the material that formed Earth. In this way, the processes occurring in these distant systems contributed directly to the composition of our own environment. The atoms that make up everyday objects have histories that trace back through generations of stars and galaxies, linking the present moment to events that occurred billions of years ago. Observing ancient galaxies also requires patience and precision. Their faint signals must be separated from closer, brighter objects, and their properties must be interpreted carefully to avoid confusion. Advances in technology have made this possible, allowing astronomers to detect increasingly distant and older galaxies. Each new observation pushes the boundary further back in time, bringing us closer to the moment when the first galaxies formed and the universe began to fill with light. Before any telescope could ever hope to capture their light, before galaxies settled into recognizable forms, and even before the universe had been enriched with the elements we now take for granted, there existed a generation of stars so different from anything we see today that they remain, in many ways, just beyond our reach. These were the population 3 stars, the very first stellar objects to ignite in the cosmos, formed from the simplest ingredients available and living out brief, powerful lives that would shape everything that followed. Unlike the stars that fill the night sky now, these earlier stars were born in a universe that contained almost nothing but hydrogen and helium. There were no heavier elements, no carbon, no oxygen, no silicon, nothing that would later help form planets or complex chemistry. The gas clouds from which these stars formed were pristine, untouched by previous generations, because there were no previous generations. This simplicity defined how they formed, how they behaved, and how they ended their lives. Without heavier elements to assist in cooling, these clouds of gas could not fragment into smaller pieces as easily as they do today. In modern star-forming regions, elements like carbon and oxygen allow gas to radiate away heat, making it easier for clouds to collapse into smaller, denser clumps that form a wide range of star sizes. But in the early universe, this cooling process was far less efficient. As a result, the collapsing gas tended to gather into much larger masses before reaching the conditions necessary for nuclear fusion. This leads to one of the most striking characteristics of population 3 stars. They were likely enormous. Many theoretical models suggest that these stars could have been tens, hundreds, or even more than 1,000 times the mass of our Sun. Such sizes are difficult to fully imagine, but their consequences are easier to understand. Larger stars burn their fuel much more quickly, producing immense amounts of energy and radiation over relatively short lifespans. These were not long-lived, steady stars like the Sun. They were intense, short-lived engines of transformation, blazing brightly and then disappearing in a fraction of the time it takes smaller stars to evolve. Their lifetimes may have lasted only a few million years, which on a cosmic scale is almost instantaneous. Yet during that brief period, they performed one of the most important roles in the history of the universe. Inside their cores, nuclear fusion began converting hydrogen and helium into heavier elements. For the first time since the Big Bang, new elements were being created, marking the beginning of chemical complexity. This process laid the groundwork for everything that would come later, from the formation of rocky planets to the chemistry necessary for life. When these stars reached the end of their lives, many did so in dramatic fashion. Some likely collapsed directly into black holes, while others exploded as supernovae, releasing vast amounts of energy and scattering newly formed elements into the surrounding space. These explosions were among the first sources of enrichment in the universe, seeding the interstellar medium with materials that would later be incorporated into new generations of stars. In this way, population 3 stars acted as both creators and distributors, transforming the simple early universe into one capable of supporting increasing complexity. Despite their importance, there is a curious challenge in studying them. No direct observations of population 3 stars have been confirmed. Their lifespans were too short, and they existed too early for their light to still be travelling toward us in a way we can easily detect. By the time the universe had aged enough for galaxies to form and stabilise, these stars had already completed their life cycles. What remains instead are indirect clues, traces left behind in the chemical composition of later stars and galaxies. One of the primary ways scientists infer the existence of these stars is by studying extremely metal-poor stars in our own galaxy. These stars, which contain very low amounts of elements heavier than helium, are thought to have formed from gas that was only slightly enriched by earlier stellar generations. By analysing their spectra, astronomers can detect patterns of elements that suggest the types of supernovae that preceded them. These patterns act as fingerprints, pointing back to the processes that must have occurred in population 3 stars, even if those stars themselves are no longer present. There is also ongoing research aimed at detecting the indirect light from these early stars through their influence on surrounding gas. As population 3 stars formed and emitted intense radiation, they would have ionized nearby hydrogen, altering the way light travels through those regions. By studying distant galaxies and the intergalactic medium, scientists hope to identify signatures of this ionization, providing further evidence of the first stellar generation. It is a subtle and challenging task, requiring careful interpretation of faint signals, but it continues to bring us closer to understanding these elusive objects. Another possibility lies in observing very distant galaxies that formed shortly after the first stars. Some of these galaxies may still contain stars that resemble population 3 stars, or at least represent transitional stages between the first generation and later populations. Observatories like the James Webb Space Telescope are capable of detecting light from these distant systems, offering a chance to study conditions that closely resemble those of the early universe. While direct detection of pure population 3 stars remains uncertain, each observation adds a piece to the puzzle, narrowing down their properties and behaviour. It is interesting to consider how different the universe would have been during the era of these stars. With no heavy elements, no dust, and no complex chemistry, the environments in which they formed were simpler, yet in some ways more extreme. The radiation they emitted would have been intense, capable of influencing vast regions of space. Their supernovae would have been among the first events to reshape the distribution of matter, driving gas outward and creating conditions for future star formation. The universe, at that time, was undergoing its first major transformations, guided by these early stellar processes. Even though population 3 stars are no longer present, their legacy is everywhere. The elements they created are part of subsequent generations of stars, part of planets, and ultimately part of living systems. The transition from a universe composed almost entirely of hydrogen and helium to one filled with a rich variety of elements began with these stars. In that sense, they are deeply connected to everything that exists today, even if they themselves cannot be directly observed. Their story also highlights the nature of cosmic history, where the most important events are not always the easiest to observe. Some of the earliest and most influential objects have left only indirect traces, requiring careful analysis and interpretation to uncover. It is a process that combines observation, theory, and patience, gradually building an understanding of events that occurred billions of years ago. The idea of ghosts we can only imagine reflects this challenge. These stars are not ghosts in a literal sense, but in the way they exist primarily in our models and reconstructions. We know they must have existed because of the evidence they left behind, yet we cannot point a telescope at them and see them directly. Instead, we piece together their story from the elements they produced, the structures they influenced, and the patterns they left in the universe's chemical and physical evolution. There is something quietly fitting about this. The oldest things in the universe are not always visible, not always present in a way that can be directly observed. Sometimes their existence is inferred, their influence traced through subtle clues that require careful attention to uncover. Population 3 stars represent this idea clearly, standing at the beginning of stellar history, shaping everything that followed, yet remaining just beyond direct observation. Somewhere within our own galaxy, not particularly far away on cosmic scales, there exists a star that has quietly endured for almost the entire history of the universe. It does not stand out in the night sky as especially bright or dramatic, and if you were to look up without guidance, you would likely pass over it without a second thought. And yet this star, known as HD 140283, carries within it a record of time so vast that it challenges the very limits of our understanding. Often referred to as the Methusela star, a name borrowed from a figure associated with great age, this object has become one of the most important reference points in astronomy for studying the early universe. Estimates place its age at around 13 billion years, meaning it formed not long after the first stars and galaxies began to appear. To put that into perspective, the universe itself is about 13.8 billion years old. so this star has been shining for nearly all of cosmic history. It has existed through the formation of galaxies, the evolution of stars, and the gradual enrichment of the universe with heavier elements, all while maintaining a steady presence within the Milky Way. What makes this star particularly fascinating is not just its age, but how we are able to determine it. Unlike counting years on a calendar, measuring the age of a star involves careful analysis of its light, its composition, and its physical properties. Astronomers study the spectrum of light emitted by HD 140283, breaking it down into its component wavelengths to identify the elements present within it. What they find is a striking lack of heavy elements, what astronomers call metals, meaning anything heavier than helium. This low metallicity indicates that the star formed at a time when the universe had not yet been significantly enriched by previous generations of stars. The absence of heavier elements is a key clue. Stars that form later in the universe's history tend to contain higher amounts of these elements, as they are created in the cores of stars and distributed through supernova explosions. By contrast, HD 140283 appears to have formed from material that had only been lightly processed, suggesting it belongs to one of the earliest generations of stars after the first population 3 stars completed their life cycles. It is not one of those first stars itself, but it formed close enough in time to carry their chemical signature, making it a kind of bridge between the earliest stellar activity and the more complex universe that followed. Determining its exact age requires combining several lines of evidence. One method involves measuring the star's luminosity and temperature, then comparing these values to models of stellar evolution. Stars change in predictable ways over time, gradually shifting their position on what astronomers call the Hertzsprung-Russell diagram, a chart that relates brightness to temperature. By locating HD 140283 on this diagram and understanding how stars of similar composition evolve, scientists can estimate how long it has been burning. Another important factor is its distance from Earth, which has been measured with high precision using instruments like the Hubble Space Telescope. Knowing the distance allows astronomers to determine the star's true brightness, which is essential for accurate age calculations. Even small uncertainties in distance can lead to significant differences in estimated age, so precise measurements are crucial. Over time, improvements in observational technology have refined these estimates, bringing them into closer alignment with the age of the universe itself. There was a time when the calculated age of HD 140283 appeared to exceed the age of the universe, creating a puzzling contradiction. Earlier estimates suggested it might be around 16 billion years old, which clearly could not be the case. This discrepancy prompted further investigation, leading to more accurate measurements and refined models. As the data improved, the star's estimated age was adjusted downward to around 13 billion years, resolving the conflict and reinforcing the reliability of modern cosmological models. This process highlights how scientific understanding evolves, with each new observation helping to refine our picture of the universe. In terms of its physical characteristics, HD 140283 is a subgiant star, meaning it is in a transitional phase between the main sequence, where stars spend most of their lives fusing hydrogen into helium, and the later stages of stellar evolution. It has already exhausted much of its hydrogen fuel in its core, and is gradually expanding and cooling as it moves toward becoming a red giant. This stage of its life provides additional clues about its age, as the rate at which stars evolve depends on their mass and composition. Despite its immense age, the star is still visible with modest equipment, located about 190 light-years away in the constellation Libra. Its relative proximity makes it an ideal candidate for detailed study, allowing astronomers to gather high-quality data about its properties. It is not among the brightest stars in the sky, but its significance lies not in its brightness, but in its history. Observing it is, in a very real sense, observing a survivor, an object that has persisted through nearly the entire lifespan of the universe. There is something quietly remarkable about the idea that this star formed when the universe was still young, when galaxies were just beginning to take shape, and yet it remains here, part of our galaxy, accessible to our instruments and our understanding. It has orbited the Milky Way for billions of years, moving through regions of space that have changed dramatically over time. Stars have formed and died around it, galaxies have interacted, and the universe has expanded, yet it continues to shine, carrying with it the imprint of its origin. Its motion through the galaxy also provides clues about its history. HD 140283 is part of the galactic halo, a region surrounding the Milky Way that contains some of the oldest stars. Unlike stars in the disk of the galaxy, which tend to follow relatively circular orbits, halo stars often have more elongated and inclined paths. This suggests that they formed early in the galaxy's history, before its structure became more settled. Studying these motions helps astronomers understand how the Milky Way assembled over time, piecing together its history from the trajectories of its oldest members. The Methusela star also serves as a kind of calibration point for our understanding of stellar ages. By studying it in detail, scientists can test and refine models of stellar evolution, ensuring that their predictions match observations. This has broader implications, as these models are used to estimate the ages of other stars and star clusters, helping to build a consistent timeline of cosmic history. In this way, a single star becomes a reference for understanding the ages of countless others, linking individual observations to the larger framework of cosmology. It is worth pausing for a moment to consider what it means for something to persist for such a length of time. This star has existed through nearly all known epochs of the universe, from the early formation of galaxies to the present day. It has witnessed, in a physical sense, the gradual transformation of the cosmos, even if it does not perceive that passage of time in the way we do. Its continued existence is a reminder that, while many objects in the universe are transient, some endure for billions of years, maintaining a continuity that connects the earliest moments of cosmic history to the present. And yet, even this star will not last forever. Like all stars, it is subject to the processes of stellar evolution, gradually changing as it consumes its remaining fuel. In time, it will expand further, shed its outer layers, and eventually become a white dwarf, a dense remnant that will cool slowly over billions of years. Its future, like its past, is governed by the same physical laws that shape all stars, reminding us that even the oldest objects are part of an ongoing cycle of change. As we continue to trace the oldest things in the universe, this star provides a valuable anchor point, a tangible example of extreme age that we can observe directly. It bridges the gap between the earliest, unobservable stars and the objects we can study in detail, offering insight into the conditions that existed shortly after the universe began to form structure. Not every star ends its life in a dramatic explosion or collapses into something extreme and difficult to imagine. Many stars, including ones not so different from our Sun, follow a quieter path, one that leads not to a sudden disappearance, but to a long, gradual fading. What remains after such stars exhaust their fuel are objects known as white dwarfs, dense stellar remnants that no longer generate energy through fusion, yet continue to exist for immense stretches of time. In many ways, these objects are among the closest things the universe has to long-lasting embers, holding on to heat and memory long after the fire that created them has gone out. To understand white dwarfs, it helps to think about the life cycle of an ordinary star. A star spends most of its existence fusing hydrogen into helium in its core, releasing energy that balances the inward pull of gravity. Over time, this hydrogen supply runs low, and the core begins to contract while the outer layers expand. The star becomes a red giant, growing significantly larger and cooler on its surface, even as its core becomes hotter and denser. Eventually, for stars of moderate mass, the outer layers are shed into space, forming what is known as a planetary nebula, a cloud of gas that drifts outward, carrying with it elements that will later contribute to new stars and planets. What remains at the centre is the core, no longer capable of sustaining fusion, yet still extremely hot and dense. This is the white dwarf. It is typically about the size of Earth, but contains a mass comparable to that of the Sun, making it incredibly dense. A teaspoon of white dwarf material would weigh tons on Earth, a consequence of the extreme compression that occurs as gravity pulls matter inward and quantum mechanical effects prevent further collapse. Specifically, it is the pressure from electrons, known as electron degeneracy pressure, that supports the white dwarf against gravity, allowing it to exist in a stable state without ongoing fusion. Unlike active stars, white dwarfs do not produce new energy. Instead, they shine by slowly radiating away the heat they retained from their earlier stages. This means they gradually cool over time, becoming dimmer and less energetic. However, this cooling process is extraordinarily slow. Some white dwarfs can take billions, even trillions of years to cool completely, far longer than the current age of the universe. Because of this, none of them have yet reached the final stage of complete cooling, which would result in a hypothetical object known as a black dwarf. The universe simply has not existed long enough for that to happen. This slow cooling process makes white dwarfs valuable tools for measuring cosmic age. By observing their temperature and luminosity, astronomers can estimate how long they have been cooling, providing an indirect measure of their age. In star clusters, where many stars formed at roughly the same time, the distribution of white dwarf temperatures can reveal the cluster's age with remarkable accuracy. The coolest, faintest white dwarfs represent the oldest remnants, offering a glimpse into the distant past of the cluster and by extension the galaxy itself. Within our own galaxy, populations of white dwarfs are found in various environments, including the disk and the halo. Those in the halo tend to be older, formed early in the galaxy's history, and they often have lower metallicity, reflecting the simpler chemical composition of the early universe. By studying these ancient white dwarfs, astronomers can trace back to periods not long after the first stars began to evolve, linking them to earlier stages of cosmic history. In this way, white dwarfs serve as quiet witnesses, preserving information about stars that no longer exist in their original form. There is also something interesting about the consistency of their behaviour. Because the physics governing white dwarfs is well understood, their cooling rates follow predictable patterns. This reliability allows scientists to use them as cosmic clocks, measuring the passage of time on scales far beyond human experience. Unlike more active stars, whose brightness and behaviour can vary significantly, white dwarfs follow a steady path of decline, making them particularly useful for studying long-term processes in the universe. Some white dwarfs exist in binary systems paired with another star. In certain cases, matter from the companion star can be drawn toward the white dwarf, accumulating on its surface. If enough material builds up, it can trigger a thermonuclear explosion known as a nova, briefly increasing the star's brightness before it settles back into its cooling state. In more extreme cases, if the white dwarf accumulates too much mass and approaches a critical limit known as the Chandrasekhar limit, it can undergo a Type 1a supernova, completely disrupting the star. These events are important for cosmology because they produce consistent brightness levels, allowing astronomers to measure distances across the universe. However, many white dwarfs remain isolated, quietly cooling over billions of years without such dramatic interactions. These solitary remnants represent the final stage of evolution for the majority of stars in the universe. Given that stars like our Sun are among the most common, it follows that white dwarfs are also abundant. Over time, as more stars exhaust their fuel, the number of white dwarfs in the universe will continue to increase, gradually shifting the balance of stellar populations toward these long-lived remnants. Considering their longevity, white dwarfs can be thought of as some of the oldest surviving stellar objects we can observe directly. While the first generation of stars has long since disappeared, their descendants, through successive generations, have left behind white dwarfs that persist to this day. Each one carries the history of its progenitor star, encoded in its composition, mass, and temperature. By studying these remnants, astronomers can reconstruct aspects of stellar evolution, tracing back through the layers of cosmic history that led to their formation. There is also a subtle connection between white dwarfs and the elements that make up our world. The outer layers expelled during the formation of a white dwarf enrich the surrounding space with heavier elements. Over time, this material becomes part of new star-forming regions, contributing to the formation of planets and eventually the conditions necessary for life. In this way, white dwarfs are part of an ongoing cycle, linking the past with the future through the continuous recycling of matter. The idea of a star ending not with a sudden disappearance, but with a long, gradual cooling, offers a different perspective on what it means for something to persist. White dwarfs do not dominate their surroundings with intense radiation or dramatic events. Instead, they quietly endure, slowly releasing the heat accumulated over their earlier lifetimes. Their presence is subtle, yet their significance is substantial, as they represent a stage that many stars will eventually reach. Even though they're relatively small compared to other stellar objects, their density and stability make them unique. The balance between gravity and electron degeneracy pressure creates a state of matter that is unlike anything encountered under normal conditions. Studying white dwarfs provides insight into the behavior of matter under extreme compression, expanding our understanding of physics in environments far removed from everyday experience. White dwarfs serve as a reminder that age is not always associated with brightness or activity. Some of the most ancient objects are also the quietest, existing in states that require careful observation to detect and understand. Their slow cooling, predictable behavior, and long lifespans make them valuable markers of cosmic time, bridging the gap between the early universe and the present. Far from the busy, swirling disk of our galaxy, beyond the familiar patterns of stars that trace the Milky Way across the night sky, there exist vast, tightly bound spheres of ancient stars that have remained largely unchanged for billions of years. These are globular clusters, dense collections of stars that orbit the galaxy like distant companions, each one containing hundreds of thousands, sometimes even millions of stars packed into a relatively small region of space. At a glance, they may appear as faint, hazy patches of light, but within them lies one of the most complete records of the early universe that we can still observe directly. Unlike galaxies, which can continue forming new stars over long periods, globular clusters are dominated by very old stars. Most of their stellar populations formed within a relatively short window of time, early in the history of the universe, and since then they have evolved together, aging as a group. This makes them particularly valuable for studying cosmic age, because instead of dealing with a mixture of stars from many different generations, astronomers can examine a more uniform population, one that reflects conditions from a specific era in the universe's past. The stars within these clusters are often more than 10 billion years old, placing their formation not long after the first galaxies began to take shape. In fact, many globular clusters are nearly as old as the Milky Way itself. Their existence suggests that they formed during the earlier stages of galaxy assembly, when gas clouds collapsed under gravity and fragmented into dense regions capable of producing large numbers of stars at once. Once formed, these clusters remained gravitationally bound, their stars orbiting a shared center, maintaining a structure that has persisted across immense stretches of time. One of the most useful features of globular clusters is the way their stars can be analysed collectively. By plotting the brightness and temperature of their stars on a Hertzsprung-Russell diagram, astronomers can determine the cluster's age with considerable precision. This method relies on identifying the point at which stars begin to leave the main sequence, the stage where they spend most of their lives fusing hydrogen into helium. Because more massive stars evolve faster, the position of this turn-off point reveals how long the cluster has existed. It is a reliable technique, and when applied to globular clusters, it consistently indicates ages that approach the earliest epochs of the universe. Among the many clusters that have been studied, one of the most well-known is Messier 13, located in the constellation Hercules. While it is not the oldest known cluster, it serves as a clear example of the dense and ancient nature of these systems. Observations of such clusters reveal not only their age but also their composition. Like the Methusela star, many globular cluster stars are metal-poor, containing very low amounts of elements heavier than helium. This indicates that they formed before multiple generations of stars had enriched the universe with heavier elements, placing them close to the beginning of stellar history. The density within a globular cluster is another defining characteristic. Stars in these clusters are packed far more closely together than in regions like our solar neighbourhood. In the central regions, the distance between stars can be only a fraction of a light year, compared to several light years between stars near the Sun. Despite this proximity, direct collisions between stars are still rare, but gravitational interactions are common. These interactions can alter stellar orbits, create binary systems, and even lead to the formation of unusual objects such as blue stragglers, stars that appear younger and hotter than the rest of the cluster, likely formed through mergers or mass transfer. The stability of globular clusters over such long periods is somewhat remarkable. They have survived the gravitational forces of their host galaxies, including tidal interactions that can strip stars away from their outer regions. Over time, some clusters do lose stars, gradually dispersing material into the galactic halo, yet many remain intact, their cores still densely populated, preserving the original structure established billions of years ago. This resilience makes them valuable archives, maintaining a record of early star formation conditions that might otherwise be lost. In addition to their role as stellar time capsules, globular clusters also help us understand the formation and evolution of galaxies. Their distribution around galaxies, including our own Milky Way, provides clues about how those galaxies assembled. Some clusters may have formed in the early stages of the galaxy itself, while others could have been captured from smaller galaxies that merged with the Milky Way over time. By studying their motions, compositions, and locations, astronomers can reconstruct aspects of galactic history, identifying past interactions and mergers that contributed to the present structure. Globular clusters are not unique to the Milky Way. Other galaxies also host their own systems of clusters, often numbering in the hundreds or even thousands. In larger galaxies, such as elliptical galaxies, these clusters can be even more numerous, forming extensive halos of ancient stars. Comparing clusters across different galaxies allows scientists to identify patterns and differences in their formation, offering a broader view of how star formation proceeded in the early universe. Observations of globular clusters have been greatly enhanced by instruments like the Hubble Space Telescope, which can resolve individual stars within these dense systems. By analysing their light in detail, astronomers can determine not only their age and composition, but also their motion and interactions. This level of detail provides insight into the dynamics of these clusters, revealing how stars move within them and how their structure evolves over time. Another interesting aspect of globular clusters is their role in testing theories of stellar evolution. Because all the stars in a cluster formed at roughly the same time, they provide a natural laboratory for studying how stars of different masses evolve. By comparing observations with theoretical models, scientists can refine their understanding of stellar life cycles, ensuring that predictions match what is seen in these ancient systems. This has broader implications, as these models are applied to stars throughout the universe, linking local observations to cosmic history. The presence of very old stars within globular clusters also reinforces the idea that some of the oldest things in the universe are still accessible to us. While the very first stars are gone, their successors remain, preserved in these dense environments. Each cluster represents a collection of stars that formed early and endured, maintaining their identities across billions of years. Studying them is not just about understanding individual stars, but about observing a population that has aged together, offering a collective memory of the early universe. There is also a sense in which globular clusters act as boundaries between different phases of cosmic history. They formed during a time when the universe was transitioning from its earlier stages into a more structured state, when galaxies were assembling and star formation was becoming more organized. Their existence marks this transition, providing a snapshot of conditions at that time. By examining them, we gain insight into how the universe moved from simplicity toward complexity, how matter gathered, and how the processes initiated by the first stars continued on larger scales. Even though these clusters are ancient, they are not entirely static. Over time, internal processes and external forces continue to shape them. Stars evolve, some becoming white dwarfs or neutron stars, while others may interact gravitationally, altering their paths. Tidal forces from the galaxy can stretch and distort the outer regions of clusters, gradually pulling stars away. These changes occur slowly, often imperceptibly on human timescales, yet they remind us that even the oldest structures are part of an ongoing process. Globular clusters offer a shift in perspective, from individual objects to entire systems that preserve history collectively. They show that age can be embedded not just in single stars, but in populations, in structures that carry the imprint of their formation across billions of years. Not everything in the universe announces its presence with light. Some of the oldest and most enduring objects are defined instead by the absence of it. They do not shine, they do not glow, and yet they persist, shaping their surroundings through gravity alone. Among these are black holes, and a class of hypothetical objects known as primordial black holes, remnants that may trace their origins back to the very earliest moments after the universe began. In a journey focused on age, these forms of darkness deserve careful attention, because what they lack in visibility, they make up for in endurance. A black hole, in its simplest description, forms when a massive star reaches the end of its life and collapses under its own gravity. If the core is heavy enough, nothing can stop the collapse, not even the quantum pressures that support white dwarfs or neutron stars. The result is an object so dense that its escape velocity exceeds the speed of light. Beyond a certain boundary, known as the event horizon, nothing can escape, not matter, not radiation, not even information in the form we usually understand it. From the outside, a black hole appears as a region of space from which no light returns, yet its presence can be inferred through its gravitational influence on nearby matter. The black holes formed from the deaths of early massive stars may be among the oldest surviving compact objects in the universe. These stars, especially those in the earliest generations, lived fast and ended quickly, collapsing into black holes that have persisted ever since. Unlike stars which burn through fuel and evolve, a black hole does not rely on energy generation to maintain its structure. Once formed, it can, in principle, exist indefinitely, changing only through interactions with its surroundings, such as accreting matter or merging with other black holes. This makes black holes uniquely suited to survive across cosmic timescales, potentially carrying forward the mass of ancient stars into the present universe. Some black holes grow over time, becoming supermassive objects found at the centers of galaxies. These supermassive black holes can contain millions or even billions of times the mass of the Sun, and their origins are still an area of active research. It is possible that some of them began as smaller black holes formed from early stars and then grew by accreting gas and merging with others. If so, then within these enormous objects lies a history that stretches back to the earliest epochs of star formation, a continuity of mass that has endured through the assembly of galaxies themselves. Observing black holes directly is not possible in the traditional sense, but their presence can be detected through their effects. Gas falling toward a black hole heats up and emits radiation, often forming a bright accretion disk that can outshine entire galaxies. In some cases, jets of high-energy particles are launched from the regions near the black hole, extending across vast distances. These phenomena allow astronomers to identify black holes and study their properties, even though the objects themselves remain hidden behind their event horizons. Through these observations, we can trace the behaviour of black holes across time, linking present-day observations to processes that began billions of years ago. Beyond black holes formed from stars, there is the possibility of something even older, objects that may have formed not from collapsing stars but directly from the conditions of the early universe. These are known as primordial black holes. Unlike stellar black holes, which require the life cycle of a star, primordial black holes could have formed within the first fractions of a second after the Big Bang, when the universe was extremely dense and fluctuations in matter could have collapsed under their own gravity. If such objects exist, they would represent some of the oldest structures in the universe, formed before stars, before galaxies, and even before atoms had fully assembled. The idea of primordial black holes is still theoretical, and their existence has not been confirmed. However, they are of great interest because they could provide insight into conditions in the early universe that are otherwise difficult to study. If they exist, they might contribute to the mysterious dark matter that makes up a significant portion of the universe's mass. Detecting them would be challenging, as they would not emit light, but their gravitational effects could reveal their presence, perhaps through lensing of distant objects, or through subtle influences on the motion of stars and gas. One of the intriguing aspects of black holes, both stellar and primordial, is their relationship with time. According to general relativity, time behaves differently in the presence of strong gravity. Near a black hole, time appears to slow down relative to distant observers. While this does not mean that black holes preserve time in a literal sense, it highlights the complex interplay between gravity and the passage of time in extreme environments. Objects falling into a black hole would appear to slow and fade as they approach the event horizon, their light stretched and redshifted, never quite crossing the boundary from the perspective of an outside observer. This effect adds another layer to the idea of black holes as enduring remnants, interacting with time in ways that differ from more familiar objects. Black holes also connect to some of the deepest questions in physics. The information paradox, for instance, arises from the question of what happens to information that falls into a black hole. If nothing can escape, does the information disappear, or is it somehow preserved? This question touches on the fundamental nature of reality, linking quantum mechanics with gravity and challenging our understanding of how the universe operates at its most basic level. While this may seem far removed from the idea of age, it reinforces the notion that black holes are not just remnants, but active participants in the ongoing exploration of physical laws. Over incredibly long timescales, black holes themselves are not entirely permanent. According to theoretical work by Stephen Hawking, black holes can emit radiation, now known as Hawking radiation, due to quantum effects near the event horizon. This process would cause them to lose mass very slowly, eventually leading to their evaporation. However, for most black holes, this process takes an extraordinarily long time, far exceeding the current age of the universe. Stellar mass black holes would take many times longer than billions of years to evaporate, and supermassive black holes would persist for durations that are almost impossible to meaningfully express in everyday terms. In practice, for the purposes of our current universe, black holes can be considered among the most enduring objects that exist. In thinking about the oldest things in the universe, black holes represent a different kind of persistence. They are not luminous like stars, nor are they composed of complex structures like galaxies. Instead, they are defined by simplicity, by mass, gravity, and the boundary that separates their interior from the rest of the universe. Their endurance comes not from ongoing processes, but from the absence of them, from a state in which change occurs only slowly over immense periods. There's also a sense in which black holes act as collectors of history. As they accrete matter, they incorporate material from their surroundings, potentially including remnants of ancient stars, gas enriched by earlier generations, and even other black holes. In this way, they accumulate a record of the processes that have occurred around them, though that record is hidden beyond the event horizon. While we cannot access this information directly, its existence adds another dimension to the idea of black holes as repositories of cosmic history. Considering primordial black holes extends this idea even further. If such objects exist, they would represent structures that have persisted since the very earliest moments of the universe, potentially carrying information about conditions that existed before the formation of any stars or galaxies. Their detection would not only confirm a new class of objects, but also provide a direct link to the universe's earliest phases, offering insight into the processes that shaped the cosmos at its beginning. Black holes and primordial remnants serve as a reminder that age in the universe is not always associated with visibility or activity. Some of the oldest objects are the most elusive, defined by their gravitational influence rather than their light. They endure quietly, shaping their surroundings and persisting across timescales that span the entire history of the universe. Not all stellar endings vanish quietly into darkness, or fade gently into long cooling embers. Some conclude in moments of extraordinary intensity, releasing more energy in a fraction of a second than entire galaxies emit over extended periods. Out of these violent endings emerge neutron stars, compact remnants forged in supernova explosions, carrying within them the memory of one of the most energetic transformations the universe allows. While their birth is brief and explosive, their existence afterward can stretch across billions of years, making them enduring relics of ancient stellar processes. A neutron star forms when a massive star, far larger than our Sun, reaches the end of its life and can no longer sustain nuclear fusion in its core. Without the outward pressure generated by fusion, gravity takes over, causing the core to collapse rapidly. As the collapse accelerates, protons and electrons are forced together under immense pressure, combining to form neutrons. The result is an object composed almost entirely of neutrons, packed so densely that its entire mass, often greater than that of the Sun, is compressed into a sphere only about 20 kilometers across. This level of density is difficult to fully grasp. A small fragment of neutron star material, no larger than a grain of sand, would weigh billions of tons on Earth. The matter inside is in a state unlike anything we can recreate under normal conditions, governed by quantum forces and extreme pressures. In this environment, atomic structures as we know them no longer exist. Instead, matter is compressed into a continuous, tightly packed arrangement of neutrons, forming what is sometimes described as neutron-degenerate matter. Despite their small size, neutron stars have powerful gravitational fields. Objects that approach them experience intense tidal forces, where differences in gravitational pull across short distances can stretch and distort matter. Their gravity is strong enough to significantly bend light, altering the paths of photons passing nearby. At the same time, neutron stars often rotate very rapidly, sometimes hundreds of times per second, creating conditions where magnetic fields become extraordinarily intense. Some neutron stars manifest as pulsars, emitting beams of radiation from their magnetic poles. As the star rotates, these beams sweep across space, and if one of them crosses Earth, it can be detected as a regular pulse of radiation. These pulses are remarkably consistent, so precise that pulses are sometimes used as cosmic clocks. Their regularity allows astronomers to measure time intervals with great accuracy, providing insight into the stability of physical processes even in extreme environments. In this way, neutron stars serve not only as remnants of past events, but also as tools for studying the nature of time and matter. The formation of a neutron star is closely tied to the supernova explosion that creates it. During this explosion, the outer layers of the original star are ejected into space, carrying with them heavy elements that were formed during the star's lifetime and in the explosion itself. Elements such as gold, platinum, and uranium are believed to be produced in these extreme conditions, making neutron star formation a key contributor to the chemical richness of the universe. The material expelled in supernovae eventually becomes part of new stars, planets, and other structures, continuing the cycle of matter that began with earlier generations of stars. Over time, neutron stars cool, gradually losing the heat generated during their formation. However, like white dwarfs, this cooling process is slow, allowing them to persist for billions of years. Their surfaces, initially extremely hot, become cooler as energy radiates away, but their cores remain dense and stable. Because they no longer rely on fusion to generate energy, their longevity is determined by the gradual release of stored heat and their interactions with their surroundings, rather than by a finite fuel supply. In some cases, neutron stars exist in binary systems, paired with another star or even another neutron star. These systems can produce a variety of phenomena, including X-ray emissions, where material from the companion star is pulled toward the neutron star and heated to high temperatures. In rare instances, two neutron stars can merge, releasing gravitational waves and producing short gamma-ray bursts, events that are among the most energetic in the universe. These mergers also contribute to the creation of heavy elements, further enriching the interstellar medium. The detection of gravitational waves from such mergers has opened a new window into studying these objects. Observatories like LIGO have confirmed the existence of these events, allowing scientists to observe the ripples in space-time produced by the collision of neutron stars. This adds another layer to our understanding, showing that these remnants are not only survivors of past events, but also participants in ongoing cosmic processes that continue to shape the universe. Neutron stars can also serve as markers of age, particularly in environments where their formation is linked to early generations of stars. In regions where star formation occurred billions of years ago, neutron stars that formed from those early populations may still exist, providing indirect evidence of ancient stellar activity. While it's often more difficult to determine the precise age of an individual neutron star compared to other objects, their presence in old stellar systems contributes to the overall picture of cosmic history. There is something distinct about how neutron stars represent time. Unlike white dwarfs, which fade slowly and quietly, neutron stars are born in dramatic events, yet afterwards settle into a stable, long-lived state. Their existence bridges two extremes: the brief, intense moment of their creation and the extended period of their persistence. This duality reflects a broader pattern in the universe, where sudden changes can give rise to enduring structures, linking moments of transformation with long-term stability. In terms of observation, neutron stars are detected through a combination of methods, including radio emissions from pulsars, X-ray observations of accretion processes, and the study of gravitational waves. Each method reveals different aspects of their behavior and structure, allowing scientists to build a comprehensive understanding of these objects. Advances in technology continue to improve our ability to detect and study neutron stars, uncovering new examples and refining our models of how they form and evolve. Their role in the broader context of cosmic age lies in their connection to earlier generations of stars. Every neutron star is the remnant of a star that once lived, burned and died, contributing to the ongoing cycle of matter and energy. By studying these remnants, we gain insight into the processes that shape the universe over billions of years, from the first stars to the present day. They are not among the very first objects to exist, but they are part of a chain that leads directly back to those earliest times, carrying forward the consequences of ancient events. Neutron stars also challenge our understanding of physics. The conditions within them push the limits of what we know about matter, requiring theories that combine quantum mechanics, nuclear physics, and general relativity. Studying them helps refine these theories, providing data that cannot be obtained in any other way. In this sense, they are not only remnants of the past, but also laboratories for exploring the fundamental laws that govern the universe. Long before stars ignited, before galaxies gathered their swirling collections of light, and even before the first structures began to take shape, the universe was already filled with something that would endure across all of cosmic history. Not large, not luminous, not dramatic in the way stars or explosions are, but fundamental and persistent. These were the first atoms, the earliest building blocks of matter, formed in the immediate aftermath of the Big Bang, and still present today in forms both simple and complex. In the earliest moments of the universe, conditions were far too extreme for atoms to exist. Temperatures were so high that matter existed as a dense plasma of particles, protons, neutrons, electrons, and photons constantly interacting and scattering. There were no stable structures, no atoms, just a rapidly expanding and cooling environment where energy and matter were tightly intertwined. As the universe expanded, however, it began to cool, and within the first few minutes, a process known as Big Bang nucleosynthesis took place. During this brief but crucial period, protons and neutrons combined to form the nuclei of the lightest elements. Hydrogen, consisting of a single proton, was the most abundant, followed by helium, which formed from combinations of 2 protons and 2 neutrons. Small amounts of lithium were also produced, along with trace quantities of other light elements. These nuclei represented the first stable forms of matter, the earliest step toward the formation of atoms as we understand them. It would take much longer, however, for these nuclei to capture electrons and form neutral atoms. For hundreds of thousands of years, the universe remained too hot and energetic for electrons to stay bound to nuclei. Only after sufficient cooling did electrons combine with these nuclei, creating the first atoms of hydrogen and helium. This moment, often referred to as recombination, marked a significant transition. Matter could now exist in a stable, neutral form, allowing light to travel freely, giving rise to the cosmic microwave background we explored earlier. These first atoms are among the oldest things that exist in the universe. Unlike stars or galaxies, which form and evolve over time, many of these atoms have persisted continuously since their creation. Hydrogen atoms, in particular, are incredibly durable. They can participate in chemical reactions, become part of stars, or drift through interstellar space. Yet the fundamental proton at their core may have existed since the first minutes of the universe. In that sense, when we observe hydrogen today, whether in distant gas clouds or within our own environment, we are encountering matter that has endured for nearly the entire history of the cosmos. The simplicity of these early elements is also important. With only hydrogen, helium, and trace lithium present, the early universe lacked the diversity of chemistry that would later emerge. There were no complex molecules, no solid materials, no planetary bodies. Yet these simple elements provided the foundation upon which all later complexity was built. Through the processes of stellar fusion, these elements would eventually be transformed into heavier ones. But the original atoms themselves often continue to exist, recycled through different environments over billions of years. Observing these ancient atoms is not limited to distant regions of space. They are present in our own galaxy, in interstellar gas clouds, and even within our solar system. The hydrogen in a drop of water, for example, contains protons that may have formed in the earliest moments after the Big Bang. While the electrons and bonds that form the molecule have changed over time, the core components of the atom can be incredibly ancient. This creates a direct connection between the earliest universe and the present, linking everyday matter to cosmic history in a very tangible way. Astronomers study these atoms through their interaction with light. Hydrogen, in particular, emits and absorbs radiation at specific wavelengths, allowing scientists to map its distribution across the universe. One of the most important of these is the 21 centimeter line, a radio wavelength emitted by neutral hydrogen. By observing this signal, astronomers can trace the presence of hydrogen gas in galaxies and in the vast spaces between them, revealing structures that are otherwise invisible. This technique provides insight into how matter is distributed, how galaxies form, and how the earliest elements continue to shape the universe. The abundance of these elements also offers strong evidence for the Big Bang model. The observed ratios of hydrogen, helium, and lithium match predictions made by models of Big Bang nucleosynthesis, providing a consistent picture of the universe's early conditions. This agreement between theory and observation reinforces our understanding of how the first elements formed and how they have persisted over time. It is a reminder that even the simplest components of the universe carry within them a record of its origin. As the universe evolved, these atoms became part of increasingly complex structures. They were drawn together by gravity, forming clouds that would eventually collapse into stars. Within those stars, nuclear fusion transformed them into heavier elements, creating carbon, oxygen, nitrogen, and others. These elements would later be released into space, contributing to the formation of new stars and planets. Despite this transformation, many of the original hydrogen atoms remained unchanged, continuing to exist alongside the products of stellar evolution. The persistence of these atoms also highlights the cyclical nature of matter in the universe. Atoms are not static. They move through different environments, becoming part of stars, then being ejected into space, then forming new structures. A single hydrogen atom might spend millions of years in a star, then drift through interstellar space, then become part of a planet or a living organism. This cycle connects different epochs of cosmic history, allowing matter to carry information and influence across vast spans of time. There is something grounding about considering the age of these atoms. While stars may burn out and galaxies may change shape, the fundamental building blocks of matter can persist. This continuity provides a sense of stability within the dynamic processes of the universe. It suggests that even as large-scale structures evolve and transform, there are elements of the cosmos that remain, linking the past to the present in a direct and measurable way. At the same time, these atoms are not isolated from change. Their interactions, their participation in chemical processes, and their role in forming new structures mean that they are constantly part of ongoing transformations. Age, in this context, does not imply inactivity, but rather endurance through change. The oldest atoms have been part of countless processes, contributing to the formation of stars, planets, and life, while maintaining their fundamental identity. The study of these elements also extends to understanding the limits of stability. Protons, which form the nucleus of hydrogen, are believed to be stable over extremely long timescales, possibly longer than the current age of the universe. If this is the case, then some of the protons that formed in the earliest moments may continue to exist far into the future, making them among the most enduring components of the cosmos. This raises interesting questions about the ultimate fate of matter and the long-term evolution of the universe. It might seem a little surprising that, after everything we've explored so far, after galaxies, stars, and dense remnants, we return once again to something simple. Not dramatic, not complex, but quietly fundamental. Because if we want to understand the oldest things in the universe, we have to spend a little more time with the first elements themselves, not just as abstract atoms, but as specific ingredients that shaped everything that followed. Hydrogen, helium, and lithium were not just early arrivals, they were the starting conditions, the initial setting from which all later structure emerged. At the beginning, these elements were not mixed into planets or locked inside stars. They existed as vast, diffuse clouds stretching across space, responding only to gravity and the gradual cooling of the universe. Hydrogen made up the overwhelming majority, simple and abundant, while helium followed as the second most common element. Lithium, by comparison, was present only in trace amounts, almost an afterthought in the early chemical balance. And yet even this small presence carried significance, offering clues about the precise conditions in those first few minutes after the universe began expanding. Hydrogen is, in many ways, the most important of these elements, not because it is complex, but because of its simplicity. A single proton, sometimes accompanied by an electron, makes up the most basic atom in existence. That simplicity allows hydrogen to persist in almost any environment, drifting through interstellar space, forming clouds and eventually collapsing under gravity to create stars. Without hydrogen, there would be no stars, and without stars, there would be no process to generate heavier elements. Its role is foundational, quietly supporting everything that comes later. Helium, slightly more complex, formed when pairs of protons and neutrons combined during Big Bang nucleosynthesis. Its presence in the early universe had a subtle but important effect. Helium does not participate in chemical bonding as readily as hydrogen, and it does not cool gas clouds as efficiently. This influenced how matter behaved as it began to collapse into the first structures. Regions rich in hydrogen could cool and condense more easily, while helium added stability without encouraging rapid fragmentation. The balance between these two elements shaped how the first stars formed, influencing their size, temperature, and lifespan. Lithium, although far less abundant, plays an interesting role in our understanding of the early universe. Its predicted abundance from Big Bang nucleosynthesis does not perfectly match what we observe in old stars today, leading to what is sometimes called the lithium problem. This discrepancy has prompted ongoing research, as scientists try to understand whether lithium was destroyed in early stellar processes, or if our models of the early universe need refinement. In this way, even a small amount of an element can carry significant implications, offering a point of tension that encourages deeper investigation into cosmic history. When we think about these elements as cosmic baby steps, it reflects the idea that the universe began with a very limited set of building blocks. There was no carbon to form complex molecules, no oxygen to support chemistry as we know it, no silicon to create rocky planets. Everything started from this simple trio, gradually evolving through processes that unfolded over billions of years. Stars formed, fused hydrogen into helium, and eventually produced heavier elements, which were then dispersed into space through supernova explosions. Each step built upon the previous one, creating a chain of increasing complexity that traces back to these earliest elements. The behavior of hydrogen, helium, and lithium in the early universe also influenced the large-scale structure we observe today. As gravity pulled matter together, regions with slightly higher density attracted more material, leading to the formation of gas clouds that would eventually become stars and galaxies. The efficiency of this process depended on how well the gas could cool, which in turn depended on its composition. Because the early universe lacked heavier elements, cooling was less efficient, leading to the formation of larger, more massive stars. This connects directly to the population 3 stars we discussed earlier, showing how the simplest elements set the stage for the first luminous objects. Even now, these elements remain widespread. Hydrogen continues to fill interstellar space, forming vast clouds that can be detected through radio observations. Helium is present in stars and gas clouds, often difficult to observe directly but essential to understanding stellar structure. Lithium, though less abundant, can still be found in certain stars, providing clues about their age and the processes they have undergone. These elements are not confined to the distant past. They are part of the present universe, continuing to participate in ongoing cycles of formation and transformation. There is also a quiet continuity in the idea that some of the hydrogen atoms around us may have existed since the earliest moments of the universe. While they may have been part of different structures over time, drifting through space, becoming part of stars or interacting with other atoms, their fundamental identity remains unchanged. This continuity creates a direct link between the beginning of the universe and the present moment, connecting the earliest conditions to the matter we encounter every day. The study of these elements extends beyond observation to precise measurement. By analysing the relative abundance of hydrogen, helium, and lithium in different regions of the universe, scientists can test models of Big Bang nucleosynthesis. The consistency of these measurements across vast distances supports the idea that the early universe was remarkably uniform, with the same processes occurring everywhere. This uniformity provides a foundation for understanding how the universe evolved, showing that even the simplest elements carry within them a record of the conditions from which they emerged. It is also worth considering how these elements interact over time. Hydrogen can combine with other atoms to form molecules, such as molecular hydrogen, which plays a key role in cooling gas clouds and enabling star formation. Helium, though less reactive, contributes to the overall mass and pressure within stars, influencing their evolution. Lithium, while less involved in large-scale processes, provides important diagnostic information, helping astronomers identify ancient stars and test theoretical models. Each element, despite its simplicity, has a role to play, contributing to the broader dynamics of the universe. The transition from a universe dominated by these simple elements to one filled with a wide range of chemical diversity is one of the most significant developments in cosmic history. It marks the shift from a relatively uniform environment to one capable of supporting complex structures. Yet this transition did not erase the original elements. Instead, they remain as a foundation, continuing to exist alongside the products of stellar evolution. This coexistence highlights the layered nature of the universe, where different stages of development are preserved within the same environment. Reflecting on these elements also brings us back to the idea of age in a more personal sense. While it is easy to think of stars and galaxies as distant and abstract, hydrogen and helium are present in more familiar contexts. They are part of the air, the water, and even the biological systems that sustain life. Recognizing their ancient origins adds another dimension to our understanding, connecting everyday experience with the deep history of the universe. Somewhere between the simplicity of individual atoms and the complexity of stars, planets, and life itself, there exists a quiet middle ground where matter begins to cooperate in more intricate ways. Not yet alive, not even close, but no longer isolated either. Atoms start to bond, to share electrons, to form structures that can persist, interact, and evolve. These are molecules, and some of the earliest ones formed long before life had any chance to emerge, drifting through space as part of a slow, ongoing process often described as stardust chemistry. Unlike the dramatic birth of stars or the explosive death that creates neutron stars and black holes, the formation of molecules is subtle. It happens in cold, dark regions of space, often within vast clouds of gas and dust known as molecular clouds. Temperatures in these regions can drop to just a few degrees above absolute zero, slowing atomic motion enough for bonds to form and persist. Under these conditions, hydrogen atoms can combine to form molecular hydrogen, the simplest and most abundant molecule in the universe. From there, more complex combinations begin to appear step by step, through interactions that are governed by physics and chemistry, rather than by any guiding force. Molecular hydrogen plays a particularly important role. It acts as a cooling agent, allowing gas clouds to lose energy and collapse under gravity. This cooling is essential for star formation, meaning that molecules are not just passive byproducts, but active participants in the creation of stars. Without molecular hydrogen, the formation of stars would be far less efficient, and the structure of the universe would look very different. In this way, even the simplest molecules contribute directly to the processes that shape galaxies and cosmic evolution. As more elements became available through stellar processes, the range of possible molecules expanded. Carbon, oxygen, nitrogen, and other elements began to combine in various ways, forming molecules such as carbon monoxide, water, ammonia, and methane. These molecules have been detected in interstellar space through their characteristic spectral signatures, allowing astronomers to map their presence across the galaxy. Each detection is a reminder that chemistry is not confined to planets or laboratories, but is an active process throughout the universe, occurring wherever conditions allow. One of the more interesting aspects of this early chemistry is how it takes place in environments that are, at first glance, extremely inhospitable. Interstellar space is vast, sparse, and cold, yet within it, molecules can form and persist for long periods. Dust grains, tiny particles composed of heavier elements, often serve as surfaces where atoms can meet and bond more easily. These grains act as catalysts, enabling reactions that might otherwise be too slow or unlikely to occur in the gas phase alone. Over time, layers of molecules can accumulate on these grains, forming icy mantles that store chemical complexity until they are later released back into space. This process leads to the formation of increasingly complex molecules, some of which are considered precursors to the chemistry of life. Organic molecules containing carbon and hydrogen have been identified in interstellar clouds and even in meteorites that have fallen to Earth. While these molecules are not alive, their presence demonstrates that the building blocks of life can form naturally in space, long before planets or biological systems come into existence. It suggests that chemistry, given enough time and the right conditions, naturally moves toward greater complexity. Observations of molecular clouds and star-forming regions have revealed a wide variety of molecules, some simple, others surprisingly complex. Radio telescopes and spectrometers allow scientists to detect these molecules by identifying the specific frequencies of light they emit or absorb. Facilities like the Atacama Large Millimeter Array have been instrumental in this work, providing detailed maps of molecular distributions and revealing the chemical richness of regions where stars are born. Through these observations, astronomers can trace the pathways of chemical evolution, linking simple atoms to more complex structures. The connection between these early molecules and later stages of cosmic development becomes clearer when we consider how material moves through the universe. Molecules formed in interstellar clouds can become part of new stars, planets, and planetary systems. During the formation of a star system, some of this material is incorporated into protoplanetary disks, where it can contribute to the formation of comets, asteroids, and planets. In some cases, molecules that formed in space may survive this process and become part of planetary surfaces, providing a chemical starting point for further development. Meteorites, for example, often contain organic molecules that formed before the solar system itself came into being. These molecules are preserved within the rock, offering a snapshot of the chemical environment that existed in the early solar nebula. By studying these samples, scientists can gain insight into the types of molecules that were present and how they might have contributed to the chemistry of early Earth. It is a direct link between interstellar chemistry and planetary processes, showing how molecules that formed in distant clouds can eventually become part of a planet's history. The idea that molecules preceded life is significant because it highlights the gradual nature of complexity in the universe. Life did not appear suddenly from nothing, but emerged from a series of steps, each building on the previous one. The formation of molecules represents one of these steps, a stage where matter begins to organize into structures capable of further interaction and development. While these molecules are not alive, they set the stage for the chemistry that would eventually lead to living systems. There is also an element of continuity in this process. The atoms that formed in the early universe, hydrogen, helium, and trace lithium, eventually participated in the formation of stars, which produced heavier elements. Those elements then combined into molecules, which in turn became part of new stars and planetary systems. Each stage feeds into the next, creating a chain of transformation that spans billions of years. Molecules are a key link in this chain, connecting the simplicity of atoms with the complexity of larger structures. In terms of age, some molecules can be remarkably old. While individual molecular bonds may break and reform over time, the atoms involved can persist across multiple environments. A molecule detected in a distant cloud may have formed millions of years ago, and its components may have existed for billions of years before that. This layered history means that even relatively simple molecules can carry a deep connection to the early universe, embodying processes that have been unfolding since the first stars began to enrich the cosmos with heavier elements. Studying these molecules also provides insight into the physical conditions of their environments. Different molecules form under different temperatures, densities, and radiation levels. By identifying which molecules are present in a region, astronomers can infer properties such as temperature, pressure, and the presence of radiation fields. This allows them to build detailed models of star-forming regions, tracing how gas and dust evolve into stars and planetary systems. Molecules in this sense act as probes, revealing information about environments that are otherwise difficult to study. The presence of complex molecules in space also raises interesting questions about the universality of chemistry. If the building blocks of life can form naturally in interstellar environments, it suggests that similar processes could occur elsewhere in the universe. While this does not imply the existence of life beyond Earth, it does indicate that the chemical pathways leading toward life are not unique to our planet. They are part of a broader cosmic process, one that unfolds wherever the necessary elements and conditions are present. If you were to sweep your hand through what appears to be empty space between the stars, you might expect to find nothing at all. A perfect vacuum, silent and clear. And yet, scattered throughout that vast darkness are countless tiny particles, so small that they would be invisible to the naked eye, drifting slowly between stars and galaxies. These are interstellar dust grains, and despite their size, they carry within them a record of cosmic history that stretches back billions of years. Unlike the atoms and molecules we've been discussing, dust grains are solid. They are made of heavier elements such as carbon, silicon, oxygen and iron, elements that were not present in the earliest universe but were forged later inside stars and distributed through supernova explosions and stellar winds. Each grain, in a sense, is a fragment of a long-gone star, condensed from material that once existed in extreme environments and then released into space where it cooled and solidified into microscopic structures. These grains form in the outer layers of aging stars, particularly red giants and asymptotic giant branch stars, where temperatures and densities allow atoms to come together into solid particles. As these stars shed their outer layers, dust is carried outward into the interstellar medium, mixing with gas and other material. Supernovae too contribute to dust production, although the violent conditions can both create and destroy grains, making their survival a balance between formation and disruption. Over time, this material spreads across space, becoming part of the diffuse environment between stars. What makes interstellar dust especially interesting is its longevity. While individual grains may be altered or destroyed over time, many survive long enough to be incorporated into new generations of stars and planetary systems. Some grains can exist for hundreds of millions or even billions of years, drifting through space, interacting with radiation, and accumulating layers of molecules on their surfaces. These grains effectively become time capsules, preserving information about the conditions in which they formed and the environments they have passed through. One of the ways astronomers detect and study dust is through its interaction with light. Dust grains absorb and scatter light, causing distant stars to appear dimmer and redder than they would otherwise. This effect, known as interstellar extinction, provides clues about the presence and distribution of dust. In addition, dust grains emit infrared radiation as they absorb energy and re-radiate it, allowing telescopes sensitive to infrared wavelengths to map their presence across the galaxy. Observatories like the Spitzer Space Telescope have been particularly useful in revealing these dusty regions, showing intricate structures where stars are forming and where dust plays an active role in shaping the environment. Dust is not merely a passive component of the interstellar medium, it actively influences the processes that occur within it. By providing surfaces on which atoms can meet and bond, dust grains facilitate the formation of molecules, including molecular hydrogen. As we discussed earlier, molecular hydrogen is crucial for cooling gas clouds and enabling star formation. Without dust, these processes would be far less efficient, and the rate at which stars form would be significantly reduced. In this way, dust grains contribute directly to the ongoing cycle of stellar birth and evolution. The surfaces of dust grains can also accumulate layers of ice, composed of molecules like water, carbon monoxide, and ammonia. These icy mantles form in cold regions of space, where temperatures are low enough for molecules to freeze onto the grain surfaces. Over time, chemical reactions can occur within these layers, leading to the formation of more complex molecules. When these grains are later heated, for example during the formation of a star, the molecules can be released back into the surrounding gas, enriching it with chemical complexity. Some of the most remarkable dust grains are those that predate our solar system. These pre-solar grains, found within certain meteorites, have been identified through their unique isotopic compositions, which differ from the material that formed the Sun and planets. These grains are believed to have originated in other stars, surviving the processes that led to the formation of the solar system, and eventually becoming incorporated into solid bodies that later fell to Earth. Studying them provides a direct link to ancient stellar environments, offering physical evidence of processes that occurred long before our solar system existed. The isotopic signatures within these grains act as fingerprints, allowing scientists to trace their origins to specific types of stars, such as red giants or supernovae. By analysing these signatures, researchers can learn about the nuclear processes that occurred within those stars, the conditions under which the grains formed, and the paths they took through space. Each grain becomes a piece of evidence, a tiny record of events that took place billions of years ago, preserved in a form that can be studied in laboratories on Earth. There is something particularly striking about the idea that such small particles can carry so much history. A single grain, no larger than a fraction of a micrometer, may have formed in the outer layers of a star, travelled through interstellar space for millions of years, become part of a molecular cloud, and then been incorporated into a meteorite that eventually landed on Earth. Its journey spans multiple stages of cosmic evolution, connecting different environments and processes in a continuous chain. The study of interstellar dust also provides insight into the early stages of planet formation. In protoplanetary disks, the disks of gas and dust that surround young stars, dust grains collide and stick together, gradually forming larger particles. Over time, these particles can grow into planetesimals and eventually into planets. This process begins with the smallest grains, showing how these tiny fragments play a role in building much larger structures. The same grains that once drifted between stars can become the foundation for entire planetary systems. Dust also influences the thermal balance of interstellar clouds. By absorbing ultraviolet and visible light and re-emitting it as infrared radiation, dust helps regulate the temperature of the surrounding gas. This, in turn, affects how clouds collapse and fragment, influencing the formation of stars. The presence of dust can shield regions from radiation, creating environments where molecules can form and persist. In these ways, dust acts as both a participant and a regulator, shaping the conditions under which other processes occur. Over long periods, dust grains are subject to various forms of alteration. They can be eroded by radiation, shattered by collisions, or incorporated into new structures. Despite these changes, some grains manage to survive, preserving aspects of their original composition. This persistence makes them valuable for studying the history of matter in the universe, providing a record that complements observations of stars, galaxies, and gas clouds. The idea of dust as a time capsule extends beyond individual grains to the broader interstellar medium. Regions rich in dust often contain material that has been recycled through multiple generations of stars, carrying the combined history of those processes. By studying these regions, astronomers can trace the flow of matter through the galaxy, understanding how elements are produced, distributed, and reused over time. As we continue to follow the thread of the oldest things in the universe, interstellar dust grains represent a transition from abstract concepts to tangible material. They are small enough to seem insignificant, yet complex enough to carry detailed information about their origins. They connect the processes of stellar evolution, molecular chemistry, and planetary formation, acting as bridges between different stages of cosmic history. Every so often, without much warning, a small piece of the universe makes its way to Earth. It does not arrive with ceremony, and most of the time it passes unnoticed, burning briefly through the atmosphere before landing quietly somewhere on the surface. These fragments, known as meteorites, are among the most accessible pieces of ancient matter we can study. Unlike distant stars or galaxies, they can be held, examined, and analysed directly, offering a tangible connection to events that occurred billions of years ago. Meteorites are not all the same. Some originate from asteroids, others from the Moon, or even Mars, but the most valuable for understanding the oldest material in the solar system are those that have remained largely unchanged since their formation. These are called primitive meteorites, or chondrites, and they formed from the original cloud of gas and dust that gave rise to the Sun and planets about 4.6 billion years ago. Because they have not undergone significant melting or differentiation, they preserve the composition of that early material, acting as a record of the conditions present at the beginning of our solar system. Within these meteorites, scientists have identified tiny spherical structures known as chondrules, as well as even older inclusions called calcium-aluminum-rich inclusions, often abbreviated as CaIs. These inclusions are particularly significant because they are among the oldest solid materials ever formed in the solar system. Radiometric dating techniques, which measure the decay of radioactive isotopes, have shown that Ca is formed approximately 4.567 billion years ago. This makes them a benchmark for determining the age of the solar system itself. What makes meteorites especially interesting in the context of the oldest things in the universe is that some of them contain material that predates the solar system entirely. Embedded within certain meteorites are presolar grains, microscopic particles that formed in the outflows of ancient stars long before the Sun existed. These grains survived the collapse of the solar nebula, the formation of planets, and billions of years of cosmic history before being incorporated into meteorites that eventually reached Earth. Their presence means that within these rocks, we have direct samples of matter that originated in environments far older than our own planetary system. The identification of these presolar grains relies on their unique isotopic signatures. Unlike most material in the solar system, which has been thoroughly mixed and homogenized, these grains retain distinct ratios of isotopes that reflect the nuclear processes of the stars in which they formed. By analysing these ratios, scientists can trace the grains back to specific types of stellar environments, such as red giants or supernovae. Each grain becomes a piece of evidence, linking laboratory measurements on Earth to events that occurred in distant stars billions of years ago. Meteorites also provide insight into the chemical processes that occurred during the early stages of the solar system. The distribution of elements and isotopes within them reveals how material was heated, cooled, and mixed as the solar nebula evolved. Some meteorites show signs of having been altered by water, indicating that even in the early solar system, chemical reactions involving liquid water were possible. This has implications for understanding how the conditions necessary for life might have developed, connecting the study of ancient matter with questions about planetary evolution and habitability. The journey of a meteorite is itself a long and complex story. Most originate in the asteroid belt, where collisions between rocky bodies can send fragments drifting through space. Over time, gravitational interactions can alter their orbits, eventually bringing them into paths that intersect with Earth. During their passage through the atmosphere, they experience intense heating, often forming a thin, dark crust on their surface. Despite this brief exposure to high temperatures, the interior of the meteorite can remain largely unchanged, preserving the ancient material within. Studying meteorites requires careful handling and analysis. Scientists use a variety of techniques, including mass spectrometry and electron microscopy, to examine their composition at very small scales. These methods allow for precise measurements of isotopes and the identification of minerals, providing detailed information about the meteorite's history. Because meteorites can be contaminated by Earth's environment, especially if they have been exposed to weathering, freshly fallen specimens are particularly valuable, offering the most accurate representation of their original state. One of the more fascinating aspects of meteorites is how they bridge the gap between distant cosmic processes and direct physical experience. While we cannot travel to ancient stars or witness the formation of the solar system firsthand, meteorites bring pieces of that history to us. Holding a meteorite, even in a controlled laboratory setting, is a way of interacting with matter that has existed for billions of years, matter that has travelled through space and survived multiple stages of cosmic evolution. The study of meteorites has also contributed to our understanding of the timing of events in the early solar system. By comparing the ages of different components within meteorites, scientists can reconstruct a timeline of formation from the condensation of the first solids to the assembly of larger bodies. This timeline helps to place the solar system within the broader context of cosmic history, showing how it fits into the sequence of events that began with the Big Bang and continued through the formation of stars and galaxies. In addition to their scientific value, meteorites carry a certain perspective. They remind us that Earth is not isolated, but part of a larger system that extends across space and time. The material that forms our planet has a history that predates its formation, connecting it to earlier generations of stars and to the processes that shaped the universe long before the solar system existed. Meteorites make this connection tangible, providing evidence that the matter around us has travelled through different environments and undergone multiple transformations. Even the frequency of meteorite falls contributes to this perspective. Small particles, known as micrometeorites, constantly rain down on Earth, adding tiny amounts of extraterrestrial material to the surface. Over long periods, this accumulation becomes significant, illustrating the continuous exchange of matter between Earth and its cosmic surroundings. Larger meteorites, though less common, provide more substantial samples, each one offering a snapshot of a different part of the solar system or a different stage of its history. Meteorites represent a point where observation becomes direct interaction. They allow us to study ancient matter not just through light or indirect signals, but through physical samples that can be analysed in detail. Their composition, structure, and isotopic signatures all contribute to a deeper understanding of how matter formed, evolved, and persisted across billions of years. Hidden within certain meteorites, far too small to notice without specialised instruments, there exist particles that carry a history older than our solar system itself. These are pre-solar grains, microscopic fragments of solid matter that formed in ancient stars long before the Sun was born. Unlike most material in the solar system, which has been melted, mixed, and reprocessed over time, these grains have remained largely intact, preserving the conditions of their origin across billions of years. In a very literal sense, they are pieces of stardust that predate everything familiar in our local cosmic environment. What makes pre-solar grains so remarkable is not just their age, but their survival. The formation of the solar system was not a gentle process. A cloud of gas and dust collapsed under gravity, temperatures rose, and much of the material was heated, altered, or destroyed as planets and other bodies took shape. Under such conditions, one might expect any delicate structures from earlier times to be erased, and yet some of these grains endured, protected within larger bodies that later became meteorites, remaining unchanged enough to retain the signatures of the stars in which they formed. These grains are incredibly small, often only a few micrometers in size, and identifying them requires careful laboratory work. Scientists isolate them from meteorites by dissolving the surrounding material with acids, leaving behind tiny resistant particles. What remains may look unremarkable at first, but when analysed, these grains reveal isotopic compositions that are unlike anything else found in the solar system. These isotopic ratios act as clear indicators that the material did not form alongside the Sun, but instead originated in much older stellar environments. The key to understanding their origin lies in these isotopic signatures. Different types of stars produce different patterns of isotopes through nuclear reactions in their cores and outer layers. For example, red giant stars and asymptotic giant branch stars generate specific ratios of carbon, nitrogen, and oxygen isotopes, while supernovae produce distinct patterns involving heavier elements. By comparing the isotopic composition of presolar grains to theoretical models and observations of stellar processes, scientists can trace each grain back to a particular type of star. In this way, each grain becomes a direct sample of a stellar environment that existed billions of years ago. There are several types of presolar grains, each associated with different stellar sources. Silicon carbide grains, for instance, are commonly linked to red giant stars, while graphite grains may originate from supernovae. Tiny diamonds, known as nanodiamonds, have also been found, likely formed under extreme conditions in stellar outflows or explosions. Each type of grain carries its own story, reflecting the processes that created it and the journey it has taken through space. The age of these grains is not measured in isolation, but inferred through their context and composition. Because they formed in stars that existed before the solar system, they must be older than 4.6 billion years. In some cases, their origins may trace back to stars that lived and died billions of years before the Sun formed, making them among the oldest solid materials known. While we cannot assign an exact age to each individual grain, their existence confirms that solid matter can persist across multiple generations of stellar evolution, surviving processes that might otherwise erase such records. Their journey through space is another aspect worth considering. After forming in the outer layers of stars or in supernova explosions, these grains were expelled into the interstellar medium, becoming part of the diffuse material between stars. Over time, they drifted through space, possibly for hundreds of millions of years, before being incorporated into the cloud of gas and dust that eventually formed the solar system. During this process, they avoided destruction, remaining intact as they became embedded within larger bodies. Eventually, some of these bodies fragmented, producing meteorites that carried the grains to Earth. This sequence of events connects multiple stages of cosmic history. A grain forms in a distant star, travels through interstellar space, becomes part of a new star system, and finally arrives on Earth, where it can be studied in a laboratory. Each step spans vast distances and timescales, yet the grain itself remains as a continuous thread linking these stages together. It is difficult to find a more direct example of how matter can persist across cosmic time, carrying with it information about environments that no longer exist. Studying presolar grains also provides insight into the processes that occur within stars. By analysing their composition, scientists can test models of nuclear fusion and stellar evolution, comparing predictions with actual samples. This helps refine our understanding of how elements are produced and distributed, contributing to a more accurate picture of cosmic chemistry. In this sense, presolar grains serve not only as relics of the past, but as tools for understanding the mechanisms that shape the universe. There is also a connection between these grains and the broader cycle of matter. The elements produced in stars are not confined to those stars. They are released into space and become part of new structures. Presolar grains represent an intermediate stage in this cycle, where material has been processed by one star and is on its way to becoming part of another system. Their presence in meteorites shows that this cycle is not just theoretical, but observable, with tangible evidence linking different generations of stars. The existence of presolar grains also highlights the limits of mixing within the solar nebula. While most material was homogenized during the formation of the solar system, these grains retained their distinct compositions, indicating that not all material was thoroughly blended. This suggests that some regions of the nebula preserved earlier material, allowing these grains to survive. Understanding how this occurred provides insight into the dynamics of the early solar system, including how gas and dust interacted and how solid bodies formed. There is a certain perspective that comes from considering these grains. They are not large or visually striking, and without careful analysis they would go unnoticed. Yet they carry information that spans billions of years, connecting the earlier stages of stellar evolution to the present. Their significance lies not in their size, but in the history they represent, a history that can be read through careful observation and analysis. In terms of the oldest things in the universe, pre-solar grains occupy a unique position. They are not as old as the first atoms, nor do they date back to the earliest moments of the universe, but they are among the oldest solid materials that can be directly studied. They provide a bridge between the abstract understanding of early cosmic processes and the tangible evidence found in meteorites. Through them, we can examine material that formed in stars long before our own, bringing the distant past into a form that can be handled and measured. Long before atoms settled into stable forms, before light was able to travel freely across space, and even before the faint glow of the cosmic microwave background began its journey, the universe released another kind of messenger. One far more elusive than light, one that barely interacts with anything at all. These are neutrinos, and among them exist a population known as the cosmic background neutrinos, particles that have been travelling through the universe since just seconds after the Big Bang. Unlike photons, which interact readily with charged particles, neutrinos are almost completely indifferent to the matter around them. They pass through stars, planets, and even entire galaxies with hardly any interaction. Trillions of them are moving through your body right now, and yet they leave no trace, no sensation, no disturbance. This ghost-like behaviour makes them extraordinarily difficult to detect, but it also allows them to preserve information from the earliest moments of the universe, carrying it forward largely unchanged. In the first second after the Big Bang, the universe was an extremely dense and energetic environment, filled with a mix of particles interacting constantly. Neutrinos were part of this early mixture, moving freely but still interacting occasionally with other particles. As the universe expanded and cooled, there came a point when neutrinos decoupled from the rest of matter. This means they stopped interacting significantly and began travelling independently through space. This event occurred much earlier than the formation of the cosmic microwave background, making these neutrinos even older messengers of the early universe. From that moment on, cosmic background neutrinos have been moving through the cosmos, largely unaffected by the structures that later formed. While photons from the early universe were scattered until recombination, neutrinos escaped almost immediately, preserving a record of conditions at a much earlier stage. In this sense, they offer a glimpse into a time that is otherwise inaccessible, a fraction of a second after the beginning, when the universe was still in a very different state. The existence of these neutrinos is not just a theoretical idea. Their presence is strongly supported by our understanding of particle physics and cosmology, and indirect evidence has been observed through their influence on the cosmic microwave background and the large-scale structure of the universe. Their properties affect how matter clump together, leaving subtle imprints that can be measured and analysed. While we have not yet directly detected the cosmic background neutrinos themselves, their effects are woven into the observations we can make, providing a consistent and coherent picture of their role in cosmic history. Detecting them directly remains one of the major challenges in modern physics. Because neutrinos interact so weakly, capturing them requires extremely sensitive detectors and innovative approaches. Facilities like IceCube Neutrino Observatory have successfully detected high-energy neutrinos from astrophysical sources, but the cosmic background neutrinos are much lower in energy, making them even harder to observe. Future experiments aim to detect them through subtle effects, such as their interaction with specially prepared materials or their influence on radioactive decay processes. Despite the difficulty in detecting them, their significance is considerable. They are among the oldest known particles in the universe, existing continuously since the earliest moments after the Big Bang. Unlike atoms, which formed later, or stars and galaxies, which took millions or billions of years to emerge, these neutrinos have been present almost from the beginning. They represent a form of matter that has persisted across all stages of cosmic evolution, from the hot, dense early universe to the structured cosmos we observe today. Their abundance is also striking. The universe is filled with these neutrinos, with an estimated number density of hundreds per cubic centimetre. Although they are nearly impossible to detect individually, their collective presence is substantial. They contribute to the overall energy density of the universe and play a role in its expansion and evolution. In this way, even though they are elusive, they are not insignificant. Their influence is subtle but widespread, affecting the behaviour of matter on large scales. There is an interesting contrast between neutrinos and photons as cosmic messengers. Photons, which make up the cosmic microwave background, interact more readily with matter and are therefore easier to detect. They provide a clear and detailed picture of the universe at the time of recombination. Neutrinos, on the other hand, offer access to an earlier period, but at the cost of being much harder to observe. Together they provide complementary views of the early universe, each revealing different aspects of its history. The idea of neutrinos as ghostly messengers reflects both their behaviour and their role. They move through the universe almost unnoticed, carrying information that is difficult to access but deeply valuable. Their existence reminds us that not all aspects of the universe are visible or easily observed. Some require indirect methods, careful analysis, and a willingness to work with subtle clues rather than direct evidence. In terms of age, cosmic background neutrinos are among the oldest entities we can consider. They formed within the first second of cosmic time and have persisted ever since. While they do not form structures in the way atoms or stars do, their presence is a continuous thread that connects the earliest moments of the universe to the present. They are not shaped by stellar processes or galactic dynamics, but by the fundamental conditions of the universe itself. Their study also highlights the interplay between different areas of physics. Understanding neutrinos requires knowledge of particle physics, cosmology, and astrophysics, bringing together concepts from different fields to build a coherent picture. This interdisciplinary approach is a hallmark of modern science, where complex questions often require insights from multiple perspectives. As we continue tracing the oldest things in the universe, neutrinos represent a step further back in time than most other objects we have considered. They take us closer to the beginning, to a stage where the universe was still in its earliest form before atoms, before stars, before galaxies. Their presence suggests that the story of cosmic age extends beyond visible matter, encompassing particles and processes that are not directly observable, but are nonetheless fundamental to the universe's history. It is one thing to point at an object and say it is old, and something entirely different to understand what that actually means. Age, in the context of the universe, is not written on surfaces or stored in simple numbers waiting to be read. It has to be inferred, reconstructed, and carefully measured using the tools of physics, observation, and reasoning. By the time we reach this point in our journey, having explored stars, atoms, dust, and even neutrinos, a natural question begins to form quietly in the background. How do we truly know how old these things are? The answer begins with time itself, not as we experience it day to day, but as a measurable dimension that can be tracked through change. In everyday life, we mark time with clocks, calendars, and cycles, but in the universe, time is revealed through processes. A star changes its brightness and temperature as it ages, radioactive elements decay at predictable rates, and light travels across space at a constant speed. These processes act as natural clocks, allowing us to estimate how much time has passed since a particular event occurred. One of the most important methods for measuring age in the universe is radiometric dating. This technique relies on the decay of unstable isotopes into stable ones over time. Each radioactive element has a characteristic half-life, the time it takes for half of a given amount to decay. By measuring the ratio of parent isotopes to their decay products, scientists can calculate how long that process has been occurring. This method is used to determine the ages of meteorites, rocks, and even some stars, providing a reliable way to anchor our understanding of time on cosmic scales. Another approach involves observing the evolution of stars. Stars do not remain static. They follow well-understood paths as they burn through their fuel. By measuring properties such as luminosity, temperature, and composition, astronomers can place stars on evolutionary tracks and estimate their ages. This method is particularly useful in star clusters, where many stars formed at the same time. By identifying where stars begin to leave the main sequence, scientists can determine the age of the entire cluster, providing a snapshot of stellar evolution at a specific moment in cosmic history. Light itself serves as a fundamental measure of time. Because it travels at a finite speed, observing distant objects means seeing them as they were in the past. A galaxy 1 billion light-years away is observed as it existed 1 billion years ago. This allows astronomers to look back across time, constructing a timeline of cosmic evolution by studying objects at different distances. It is a method that does not require direct measurement of age, but instead uses distance as a proxy for time, creating a layered view of the universe's history. The cosmic microwave background provides another key reference point. As the oldest light we can observe, it acts as a baseline for measuring the age of the universe itself. By analysing its properties, scientists can determine the rate of expansion and the composition of the universe, leading to precise estimates of its age. This, in turn, allows other objects to be placed within a broader timeline, ensuring that our measurements remain consistent across different methods. There is also a role for theoretical models in understanding time. Observations alone are not always enough. They must be interpreted within the framework of physics. Models of stellar evolution, nuclear synthesis, and cosmic expansion provide the context needed to translate observations into ages. These models are constantly refined as new data becomes available, improving their accuracy and reliability. The process is iterative, with theory and observation working together to build a coherent picture of the universe's history. An important aspect of measuring age is uncertainty. No measurement is perfectly precise, and each method comes with its own limitations. Distances may have small errors, models may rely on assumptions, and observational data may be incomplete. Recognizing and accounting for these uncertainties is a crucial part of scientific practice. Over time, as techniques improve and more data is collected, these uncertainties can be reduced, leading to more accurate and consistent estimates. The concept of time in the universe is also influenced by relativity. According to Einstein's theory of general relativity, time is not absolute, but can vary depending on gravity and motion. In regions of strong gravitational fields, such as near black holes, time can pass more slowly relative to distant observers. While these effects are usually small in most cosmic environments, they become significant in extreme cases and must be taken into account when making precise measurements. This adds another layer of complexity to our understanding of time, showing that it's not a simple, uniform backdrop, but a dynamic aspect of the universe. In considering the role of time, it is helpful to think of it not just as a measure of duration, but as a record of change. Every object we have discussed carries within it evidence of processes that have occurred over time. The composition of a star reflects the elements it has fused. The structure of a galaxy reflects its history of interactions, and the isotopic ratios in a meteorite reflect its formation and evolution. Time is encoded in these features, waiting to be interpreted through careful observation and analysis. There is also a connection between time and memory, not in a conscious sense, but in the way physical systems retain information about their past. A white dwarf cools in a predictable way, preserving a record of how long it has been radiating heat. A globular cluster retains a population of stars that form together, allowing its age to be determined. Even the cosmic microwave background preserves fluctuations from the early universe, acting as a kind of imprint of its initial conditions. These forms of memory allow us to reconstruct history, turning observations into timelines. As we move through different scales from particles to galaxies, the methods of measuring time adapt, but the underlying principle remains the same. We look for processes that change in predictable ways and use them as references. This approach allows us to build a consistent framework where different measurements reinforce each other, creating a coherent understanding of cosmic history. The agreement between different methods, radiometric dating, stellar evolution, and cosmological observations, strengthens our confidence in the timeline we have constructed. The role of time also extends to how we interpret the concept of oldest. An object can be considered old in different ways, depending on what aspect we're measuring. A star may be old in terms of its age since formation, while an atom may be old in terms of how long its components have existed. A particle like a neutrino may be older still, tracing back to the earliest moments after the Big Bang. Understanding these distinctions is important, as it allows us to compare different objects within a common framework, recognizing that age can be defined in multiple ways. There is a quiet shift that happens when we begin to think of time this way. It becomes less about counting years and more about tracing processes, less about fixed numbers and more about relationships between events. The universe does not keep time in the way we do, but it does record its history through the behavior of matter and energy. By learning to read those records, we gain access to a timeline that spans billions of years, connecting the earliest moments to the present. Before anything in the universe can be called the oldest, there has to be a way to measure age with some confidence, some consistency, and some connection to physical reality. Otherwise, the idea of age becomes vague, almost meaningless, drifting without anchor. What makes our understanding of the universe so powerful is that we do not rely on a single method, but on several independent approaches that all point toward the same timeline. Each method has its own strengths, its own limitations, and its own perspective on time. Yet together they form a coherent system that allows us to trace events back billions of years. One of the most grounded methods begins not in the stars, but in matter itself, through the process of radioactive decay. Certain elements are unstable, meaning their atomic nuclei will naturally transform into more stable forms over time. This transformation happens at a predictable rate, described by a half-life. For example, uranium slowly decays into lead over billions of years. By measuring how much uranium remains compared to how much lead has formed, scientists can determine how long that process has been taking place. This method, known as radiometric dating, is particularly useful for studying meteorites and the oldest rocks. Because these materials have remained relatively unchanged since their formation, they provide reliable records of early events. When applied to the oldest meteorites, radiometric dating consistently yields ages of around 4.567 billion years, marking the formation of the solar system. This provides a firm starting point, a kind of timestamp that anchors our local cosmic history within the broader timeline of the universe. Moving beyond solid matter, another approach relies on the behavior of stars. Stars evolve in predictable ways, governed by the physics of nuclear fusion and gravity. By observing a star's brightness, temperature, and composition, astronomers can estimate its stage of evolution, and, from that, its age. This method becomes especially powerful when applied to groups of stars, such as globular clusters, where all the stars formed at roughly the same time. By identifying the point at which stars begin to leave the main sequence, scientists can determine how long the cluster has existed. This technique has revealed that some globular clusters are more than 12 billion years old, placing them among the oldest structures in the galaxy. The consistency of these measurements, across different clusters and different methods, reinforces their reliability. It also provides a bridge between local observations and the larger history of the universe, showing that the oldest stars formed relatively soon after the Big Bang. Another method, one that feels almost intuitive once understood, is based on the finite speed of light. Because light takes time to travel, observing distant objects means seeing them as they were in the past. A galaxy located 1 billion light-years away appears as it did 1 billion years ago. By observing objects at different distances, astronomers can effectively look back through time, constructing a sequence of events that traces the evolution of the universe. This approach does not measure age directly in the way radiometric dating does, but it provides a powerful way to observe different stages of cosmic history. It allows scientists to study the formation of galaxies, the behavior of early stars, and the conditions of the universe at various points in time. By combining observations from different distances, a timeline emerges, one that connects the earliest observable structures to the present day. The expansion of the universe adds another layer to this method. As space itself expands, light travelling through it is stretched, shifting toward longer wavelengths in a process known as redshift. By measuring this redshift, astronomers can determine how much the universe has expanded since the light was emitted. This provides a way to estimate distances and, by extension, the time at which the light was released. It is a subtle but powerful tool, linking the geometry of the universe to the passage of time. At the largest scale, the cosmic microwave background provides a kind of universal reference point. By analysing its temperature fluctuations and distribution, scientists can determine key properties of the universe, including its age, composition, and rate of expansion. The current estimate of approximately 13.8 billion years for the age of the universe is based largely on these observations. This serves as the upper limit for the age of any object within the universe, a boundary within which all other measurements must fit. There are also more specialised methods used in particular contexts. White dwarfs, for example, cool over time in a predictable way. By measuring their temperature, astronomers can estimate how long they have been cooling, providing another way to determine age. Similarly, neutron stars can be dated through their rotation rates and magnetic field decay, although these methods are more complex and less precise. Each approach contributes a piece to the overall puzzle, offering insights that complement other techniques. What makes these methods especially compelling is how they converge. Radiometric dating, stellar evolution, light travel time, and cosmological observations all point toward a consistent timeline. This convergence is not accidental. It reflects the underlying consistency of physical laws across the universe. Different processes, governed by the same principles, produce results that align with one another, reinforcing the reliability of our measurements. Of course, no method is without uncertainty. Measurements of distance can be refined, models of stellar evolution can be adjusted, and new data can lead to revisions. Science is not static, and our understanding of age continues to improve as new observations are made. However, the overall framework remains robust, supported by multiple lines of evidence that agree within known margins of error. There is also an interesting relationship between precision and scale. On smaller scales, such as within the solar system, we can measure ages with remarkable accuracy, often within a few million years. On larger scales, such as the age of the universe, the uncertainties are greater, but still relatively small compared to the total time span involved. This balance allows us to place objects within a coherent timeline, even when exact numbers may vary slightly depending on the method used. Understanding how we measure age also changes how we think about the oldest things in the universe. It is not simply a matter of finding the largest number, but of understanding the processes that define age in different contexts. A particle that has existed since the early universe may be older in one sense, while a star that has persisted for billions of years may be older in another. The methods we use help clarify these distinctions, allowing us to compare different objects within a shared framework. There is a quiet confidence that emerges from this understanding, not certainty in every detail, but a well-supported picture of the universe's history, built from observations that span a wide range of scales and processes. Each method reinforces the others, creating a network of evidence that points toward a consistent narrative from the earliest moments after the Big Bang to the present day. At some point after following atoms back to their beginnings, tracing light across billions of years, and considering particles that have existed since the first seconds of the universe, the question begins to change. It is no longer only about identifying what is oldest, but about understanding what we mean when we use that word. Because oldest in the universe is not as simple as it first appears. It depends on definitions, on perspective, and on what exactly we are choosing to measure. When we say something is old, we usually imagine a continuous existence, something that has persisted unchanged from its origin to the present. But in the universe, very few things remain truly unchanged. Stars evolve, galaxies merge, atoms combine and separate, and even particles can shift states or interact in ways that alter their context. This raises a quiet question. Does something remain the same object if it has passed through many transformations, or is age tied to the continuity of its fundamental components? Consider a hydrogen atom. Its proton may have formed within the first minutes after the Big Bang, making it incredibly old. Yet that proton may have spent time inside a star, been part of a molecule, drifted through interstellar space, and eventually become part of a living organism. Is the atom itself the same entity throughout this journey, or is its identity shaped by the roles it plays along the way? If we define age as the time since its fundamental components came into existence, then it is among the oldest things imaginable. But if we define age as the time since its current arrangement formed, then its age may be much younger. A similar question arises with stars. A star like HD 140283 has existed for nearly the entire history of the universe, making it one of the oldest observable stars. Yet the material that makes up that star may be even older, having been part of earlier cosmic processes. In this case, the star itself has a clear beginning, but its components have a deeper history. Which of these should we consider when thinking about age? The object as a whole, or the matter that composes it? Particles like neutrinos push this question even further. If cosmic background neutrinos have been travelling since the first seconds after the Big Bang, then they represent some of the oldest entities in existence. They have not formed into larger structures, have not participated in the same cycles of transformation as atoms and stars, and have largely remained unchanged. Does this make them more ancient in a meaningful sense, or simply more isolated from the processes that create complexity? There is also the matter of visibility. Much of what we have explored cannot be seen directly. We infer the existence of early stars, we detect the influence of neutrinos, and we analyse tiny grains of dust to reconstruct events that occurred billions of years ago. The oldest things in the universe are often the hardest to observe, not because they are rare, but because they do not interact strongly with light or other forms of energy. This creates a subtle shift in perspective, where the most ancient objects are not the most obvious, but the most elusive. Another way to approach the question is to think in terms of continuity versus change. Some objects, like white dwarfs or neutron stars, represent the end states of stellar evolution. They are stable, long-lived, and relatively unchanging compared to the stars that preceded them. Others, like molecules or dust grains, are constantly being formed and destroyed, participating in cycles that prevent them from maintaining a continuous identity over long periods. Age in this sense becomes tied to stability, to the ability of an object to persist without being fundamentally altered. Yet even stability has limits. Black holes, which we considered earlier, may persist for extraordinarily long times, but even they are subject to gradual processes like Hawking radiation. Over timescales far beyond the current age of the universe, they too may change and eventually disappear. This suggests that nothing is truly permanent, that even the oldest things are part of a larger process of transformation. Age, then, is not about permanence, but about duration within a system that is constantly evolving. There is also a human element to this question. Our sense of age is shaped by our own experience, by lifespans that are short compared to cosmic timescales. When we speak of billions of years, we're already stretching beyond intuitive understanding. The difference between 1 billion and 10 billion years is difficult to feel, even if we can calculate it precisely. This means that our language and concepts are always approximations, tools that help us navigate ideas that are far larger than everyday experience. Thinking about the oldest things in the universe can also shift how we see the present. If the matter around us has existed for billions of years, if the atoms in our bodies were once part of stars, then the boundary between past and present becomes less distinct. The past is not gone in the way we might imagine. It is carried forward in the material of the universe, in the light that reaches us, and in the structures that persist over time. Age becomes a kind of continuity, linking moments across vast spans of time. There is a quiet balance between simplicity and complexity in this perspective. The simplest things, like fundamental particles, may be the oldest, yet they do not form the complex structures we associate with the universe. More complex objects, like stars and galaxies, arise later, building on the foundation established by those simpler components. The oldest does not necessarily mean the most complex, and the most complex does not necessarily mean the oldest. Understanding this distinction helps clarify what we're really asking when we search for the oldest thing. It is also worth considering that the question itself may not have a single answer. Depending on how we define thing, we might arrive at different conclusions. If we focus on particles, neutrinos and protons may be among the oldest. If we focus on observable structures, ancient stars and globular clusters take that role. If we consider solid matter, presolar grains and meteorites provide direct evidence of early cosmic history. Each answer is valid within its own context, reflecting the different ways we can interpret age. This plurality of answers does not weaken the question, but rather enriches it. It shows that the universe can be understood from multiple perspectives, each offering its own insights. By exploring these perspectives, we gain a more complete picture of cosmic history, one that includes both the earliest moments and the ongoing processes that shape the universe today. Right here, in the quiet of this moment, surrounded by familiar things that feel immediate and present, it is easy to forget that nothing around us is truly new. Not in the way we might instinctively think. The objects in a room, the air you are breathing, even the atoms that make up your own body, all carry histories that stretch far beyond anything we can directly remember. When we talk about the oldest things in the universe, it can feel distant, abstract, something belonging entirely to deep space and ancient time. But there is a more subtle truth unfolding beneath that idea. Those ancient things are not just out there, they are here. Take a slow breath for a moment and consider what that air actually is. The oxygen entering your lungs was formed inside stars, likely in multiple generations of them, before being released into space and eventually becoming part of Earth's atmosphere. The hydrogen in the water you drink traces back even further, to the earliest moments after the Big Bang, when the first protons formed. These atoms have travelled, transformed, and combined over billions of years, and yet they are part of your present experience right now. The past is not separate from the present. It is woven directly into it. This connection becomes clearer when we think about how matter moves through the universe. Nothing stays in one place forever. Gas drifts through interstellar space, collapses into stars, is ejected again through stellar winds or supernova explosions, and then becomes part of new structures. Planets form from this recycled material, and within those planets, chemistry unfolds in increasingly complex ways. At each stage, matter is reused, reshaped, and redistributed, but it does not begin from nothing. It carries its history forward, layer by layer. Even something as solid as a rock on Earth has a story that reaches back into cosmic history. The elements within it, iron, silicon, oxygen, were formed in stars long before the sun existed. Those elements were part of the cloud that collapsed to form the solar system, eventually becoming part of the Earth's crust. Over time, geological processes reshaped that material, but its origin remains tied to events that occurred billions of years ago. Holding a stone, in that sense, is holding the result of an extended chain of transformations that began in distant stars. Meteorites make this connection even more direct. As we explored earlier, these objects can contain pre-solar grains, fragments of matter that formed in ancient stars and survived the formation of the solar system. When a meteorite lands on Earth, it brings with it material that has travelled across space and time, preserving evidence of environments that no longer exist. Studying these objects is not just about understanding the past in an abstract way, but about interacting with it physically, examining samples that carry within them a record of cosmic history. There is also a connection through light. Every time we look at the night sky, we are seeing the past. The light from distant stars and galaxies has taken years, centuries, or billions of years to reach us. Even the light from the sun takes about 8 minutes to arrive, meaning that what we see is always slightly delayed, always a glimpse of what has already happened. This delay is usually too small to notice in everyday life, but on larger scales, it becomes a powerful reminder that observation is always tied to time. The idea that the present is built from the past extends beyond physical matter to the structure of the universe itself. Galaxies have grown through mergers, stars have formed and died, and the distribution of matter has changed over time. The Milky Way, the galaxy we are part of, is the result of billions of years of accumulation and interaction. Its current form reflects a long history of smaller systems coming together, stars evolving, and material being redistributed. When we look at the galaxy, we're seeing not just its present state, but the outcome of processes that began long ago. There is also a more subtle connection through the laws of physics. The same principles that governed the early universe continue to operate today. The behaviour of atoms, the speed of light, the force of gravity, these have not changed over time. This consistency allows us to interpret observations of distant objects and apply the same understanding to local phenomena. It creates a continuity between the earliest moments of the universe and the present, showing that the same rules apply across all scales and times. Thinking about this connection can shift how we perceive age. Instead of seeing the oldest things as separate from us, existing only in distant space or ancient time, we begin to see them as part of a continuous process that includes the present. The atoms in your body, the light you see, the objects around you, all participate in this process. They are not isolated from the universe's history, they are expressions of it. There is also something grounding in this realization. The idea that we are connected to the earliest moments of the universe, not metaphorically, but physically, through the matter that composes us. It suggests that the story of the universe is not something we're merely observing from the outside, but something we are part of. Our existence is linked to processes that began billions of years ago, and the matter we are made of will continue to exist long after our individual experiences end. At the same time, this perspective does not diminish the present. Instead, it enriches it. Knowing that the atoms around us have such deep histories adds a layer of meaning to ordinary experiences. It turns simple observations into connections with the past, showing that even the most familiar things carry within them a record of cosmic evolution. The present becomes a point where many different timelines converge, where ancient matter and current processes meet. Somewhere along this journey, without any clear boundary marking the shift, the question we started with begins to feel a little different, not because it has been answered in a simple way, but because it has unfolded into something broader, something that stretches beyond a single object or a single moment. What is the oldest thing in the universe? At first, it sounds like a question with a clear destination. By now, it feels more like a quiet landscape, where different answers exist side by side, each one true in its own way. If we look at the earliest particles, those that have existed since the first seconds after the Big Bang, then neutrinos and protons stand among the oldest known entities. They have persisted almost unchanged, moving through the universe, largely untouched by the processes that created stars and galaxies. In terms of continuous existence, they represent a direct link to the beginning, a kind of uninterrupted presence that spans nearly all of cosmic time. If instead we turn our attention to atoms, particularly hydrogen, we find another kind of age. These atoms formed shortly after the universe cooled enough to allow stable structures, and many of them still exist today. They have participated in countless transformations, becoming part of stars, drifting through space, forming molecules, and eventually contributing to planets and living systems. Their age is not defined by isolation, but by continuity through change, a different way of persisting across time. Looking at stars, objects like HD 140283 offer a more tangible sense of age. These are objects we can observe directly, stars that have been shining for billions of years, carrying within them the chemical signatures of the early universe. They provide a bridge between abstract concepts and observable reality, allowing us to see something that has endured across most of cosmic history. Then there are the remnants, white dwarfs, neutron stars, black holes, each representing a different kind of persistence. Some cool slowly, fading over immense timescales. Others remain compact and stable, their structure defined by extreme physical conditions. Black holes, perhaps the most enduring of these, may persist for durations far beyond the current age of the universe, slowly evolving over timescales that are difficult to fully comprehend. And scattered among these larger structures are the smallest carriers of history. Pre-solar grains, molecules, dust particles, fragments of matter that formed in ancient stars and survived to become part of meteorites, part of planets, part of the material we can study directly. These are pieces of the past that we can hold, examine and understand, not through distant observation, but through direct interaction. When all of these perspectives are placed together, the idea of the oldest thing becomes less about a single answer and more about a layered understanding. Age in the universe is not a single dimension. It depends on what we are measuring, whether it is the time since formation, the continuity of existence, or the persistence of fundamental components. Each perspective highlights a different aspect of cosmic history, and together they create a more complete picture. There is also something calming in this realization. The universe does not rush. Its processes unfold over billions of years, guided by consistent laws that operate without urgency. Stars form, evolve, and fade. Matter cycles through different states. Particles continue their quiet journeys. Nothing is hurried, and nothing is truly isolated from the larger whole. Everything is part of a continuous flow, a sequence of events that connects the earliest moments to the present and beyond. If you think back to where you are right now, wherever you happen to be listening, there is a gentle shift that can happen. The room around you, the objects nearby, the air, the light, none of it is separate from this story. The atoms that make up everything you can touch have histories that stretch far beyond this moment. They have been part of stars, part of clouds of gas, part of processes that unfolded long before Earth existed. The present is not detached from the past, it is built from it. There is no need to hold all of this in a precise or detailed way. It is enough to let the idea settle quietly, that the universe has been unfolding for billions of years, and that the matter around you is part of that unfolding. The oldest things are not just distant or abstract. They are part of the same fabric that makes up everything we experience. As this exploration comes to a gentle pause, the question remains, but it no longer feels like something that needs a single, final answer. Instead, it becomes a way of looking at the universe, a way of noticing the depth of time contained within even the simplest things. The oldest thing in the universe is not just one object, but a collection of enduring elements, particles, atoms and structures, each carrying its own story, each connected to the same beginning. And from here, the story does not end. It continues, slowly and steadily, as it always has, with matter moving, light travelling, and time unfolding in ways that are both vast and quiet at the same time.